How did a giant planet like 51 Pegasi b end up orbiting so blisteringly close to its star? Why did the discovery of this hot Jupiter shatter old ideas about how planets form and move? What new vision of planetary systems did this faint wobble in starlight open for us? Picture the quiet stillness of a night sky in 1995, with distant stars winking softly overhead and a faint band of the Milky Way stretching across the darkness. The air hums with anticipation and wonder, as if something magical is about to be discovered. Two astronomers sit together in a small hilltop observatory, quietly consulting their instruments and taking careful notes. They peer through their telescope at one particular star that has long burned with a familiar, steady glow. This star is called 51 Pegasi, a sun-like star about 50 light-years away, quietly looking down on our own little planet, Earth. Above them, the Milky Way seems to hold its breath, its countless stars watching silently. It is an ordinary night at first, still and calm, but a gentle sense of possibility lingers. Above them, the Milky Way seems to hold its breath, its countless stars watching silently. Little do they know, the universe is already stirring with a new and surprising secret. In the deep silence of the night, even the faintest change can carry great significance. And on this night, something extraordinary is about to unfold. For a long time, astronomers searched in vain for planets around other stars. Many theories predicted that most stars should be surrounded by planets, much like our Sun is surrounded by its family. But the evidence remained elusive. The few worlds known outside our own system were orbiting exotic dead stars, called pulsars, not shining suns like ours. Those pulsar planets were fascinating discoveries, but hardly the kind of planetary systems most people had imagined. Around ordinary sun-like stars, none had been confirmed yet, despite decades of searching. The first confirmed exoplanets had been found in 1992, orbiting a pulsar, a dead stellar remnant. But those exotic worlds, bathed in deadly radiation, were the only examples. No one had yet found a world orbiting a normal, shining star. By the mid-1990s, advances in technology gave hope. Teams around the world built ever more precise spectrographs to detect the slightest wobble in a star. One such instrument, called ELODY, was operating in France under a Swiss team. 51 Pegasi was a bright, sun-like star, a natural choice for close observation. 51 Pegasi happens to be relatively nearby and bright in our night sky. 51 Pegasi was chosen because it was similar to our Sun and easy to observe. Night after night, Michel Mayor and Didier Queloz of the Geneva Observatory began collecting data on this star. They watched 51 Pegasi with patient curiosity, waiting for any hint of a hidden companion. The star itself, 51 Pegasi, sits in the constellation Pegasus, the winged horse of Greek myth. It is relatively nearby in cosmic terms, only about 50 light-years from Earth. The designation 51 means it was the 51st star catalogued in that constellation. When the planet was discovered, it was given the provisional name 51 Pegasi b, later nicknamed Dimidium. Years later, the planet received the official name Dimidium, Latin for half, in recognition of its mass being roughly half that of Jupiter. The host star, 51. Pegasi itself is an ordinary yellow star, much like our Sun in size and brightness. It lies about 50 light-years away, which means its light takes 50 years to reach us. Its temperature is slightly cooler than the Sun's, and its spectrum shows it has a bit more of the heavier elements than our Sun. This extra richness in elements may have helped it form planets, These observers were seasoned astronomers at the Geneva Observatory who long regarded the night sky as a grand library of secrets. They were men of quiet curiosity, believing the sky had stories waiting to be told. On this night, they expected nothing dramatic, just carefully monitoring subtle patterns in the starlight. They listened with great patience to faint signals in the star's light. Their telescope and spectrograph were delicate instruments, attuned to the whispers of distant worlds. They sat quietly together, observing in companionable silence. Outside, the night remained calm and still, as if the world was pausing to listen along with them. These scientists had an unshakable belief that the universe had secrets to reveal, even when all seemed quiet. Late that night, the observatory was filled with a hush. Through the dome's slit, the stars glittered, while the Swiss Alps slept around it. Meyer and Queloz sat side by side before a glowing screen. Their eyes were trained on the series of spectral lines that Elodie recorded from 51 Pegasi. Each night's data flickered in front of them, and they carefully entered values into their log. In that dim light, a slight groove on one chart line stood out. They paused, heartbeats matching, as the graph revealed the star's gentle wobble. It was a subtle curve in the data, but unmistakable once seen. For a fleeting moment, neither spoke. The feeling was electric, yet serenely quiet, as if they were witnessing something profound in a whisper. They spent the next hours double-checking every number. Every wobble, every peak in the data was scrutinized. Despite fatigue, they stayed alert. This could be a monumental find. Gradually, their initial excitement turned to conviction. The pattern was real, and it meant they were observing a planet tugging at its star. Excitement welled up quietly in them as the realization sank in. The night gave way to dawn, and with it, the world would soon know of their discovery. In that quiet observatory, excitement finally bloomed. Meyer and Queloz exchanged smiles, realizing they were witnessing something historic. They felt a quiet jubilation, not loud applause, but a deep, happy glow of discovery. Years of work had paid off with a tiny wobble on the screen. They knew they had uncovered something never seen before. A planet beyond our solar system, just around the corner of the universe. They knew this moment would be remembered, a quiet triumph long after they had gone home. Once they were certain, Meyer and Queloz announced their findings to the world. They took care to explain their methods clearly, knowing other scientists would scrutinize every detail. They submitted their results to a scientific journal, and soon the news broke internationally. Science magazines and newspapers ran headlines about the first alien planet around a sun-like star. Everyone realized this was a historic milestone. In hindsight, that humble wobble in the data had rewritten our place in the universe almost overnight. After the announcement, other teams immediately reviewed their observations. Within months, more telescopes found additional hot Jupiters. In one famous case, astronomers watching a different star noticed a similar wobble and confirmed it by transit. Across the globe, teams of astronomers quickly looked through their own data for similar planets. The floodgates were open, and suddenly the calendar was filled with new discoveries. Each one reaffirmed that 51 Pegasi b was not alone, and that astronomers had opened a door to a vast hidden population of strange planets. Over many nights, they gathered data, letting the slight tremors in starlight accumulate. Slowly, a pattern emerged in that tiny wobble of 51 Pegasi. Each observation confirmed it repeated in a steady rhythm. It was as if 51 Pegasi was performing a silent, deliberate dance with an unseen partner. The planet raced around its star once every 4 Earth days. They even corrected for Earth's motion and other influences, ensuring the wobble truly came from 51 Pegasi. Piece by piece, a clear pattern emerged. What could be powerful enough to tug on a star with such a rhythm? There was only one plausible answer. Something with significant mass was orbiting very closely. In the vast emptiness of space, gravity is the hidden choreographer. Even a planet, if massive enough and near enough, can make a star quiver. In that moment of clarity, the pattern became undeniable. To Mayer and Queloz, it felt like unlocking a door in the cosmos. All at once, a new world was there in their sights. The scientists realized they had found something extraordinary, a hidden world, revealed only by this gentle tug. News of the discovery spread quickly, and many astronomers were astonished. The idea of a giant planet so close to its star was completely unexpected. It violated the old patterns, like hearing a favorite melody suddenly change tune. At first, some skeptics even wondered if the data could be wrong. Astronomers began to rush through their routines with excitement, reopening old notebooks and combing through data they once thought ordinary. The notion that nature could surprise even the most careful scientist became clear. But the signals held firm, forcing everyone to admit that the universe had found a way to surprise us once again. The discovery of 51 Pegasi b forced astronomers to rethink their theories. In the years that followed, scientists proposed new explanations. Maybe this giant had formed far from its star and migrated inward over time, pulled by the gravitational pull of the protoplanetary disk or interactions with other planets. Today, the idea that planets can migrate is well accepted. The simple picture of planets forming and staying in one place had to be revised. Suddenly, the idea that a planet might roam through its system became part of the conversation. The discovery of 51 Pegasi b, in effect, opened the door to understanding that destiny can move a planet across the system. The textbook picture of a static solar system had to expand into a dynamic view. 51 Pegasi b had upended the old rulebook of planet formation. When their analysis was complete, the true nature of the planet became clear. It was enormous, roughly half as massive as Jupiter, our own system's giant, yet its orbit was astoundingly small. It was a true behemoth, trapped in a tight orbit around 51 Pegasi. It constantly bathed in the star's intense glare. The planet raced around its star once every 4 Earth days. For perspective, in our own solar system, Earth takes 365 days, and even Mercury takes 88 days to orbit the Sun. This world, by contrast, was completing a year in the time we might take a long weekend. A planet of Jupiter's size so close to its star seemed almost impossible under the old theories of planetary systems. It dwarfed all that had come before it in exoplanet discovery. One can only imagine the pressure deep inside such a world. If it has a core, it must be under crushing weight. Because of its size and composition, this planet is called a gas giant, similar to Jupiter. At first, these worlds were sometimes dubbed Pegasids, after 51 Pegasi, but the name Hot Jupiter eventually stuck, capturing the idea of a Jupiter-like world in a blazing close orbit. Its bulk is mostly hydrogen and helium, as in our own giant planets, likely with a dense core of heavier elements buried deep below its swirling clouds. This planet's mass is about half of Jupiter's, roughly 150 times that of Earth. It is difficult to imagine such a massive planet residing so close to its star. It is as if the planet's atmosphere is bloated, puffed up by the unceasing furnace of the star. Interestingly, its radius is somewhat larger than Jupiter's, meaning it is less dense. This inflation is a result of the intense heat it absorbs from its star, which puffs up its atmosphere. It is as if the planet's atmosphere is bloated, puffed up by the unceasing furnace of the star. Despite these extreme conditions, We can learn much about its nature by studying such planets, piecing together clues about their interior and formation. It was a true giant world, and its size amazed the discoverers. This world dwarfed all that came before it. Even its gravity at the cloud tops would be crushing, hundreds of times stronger than Earth's gravity, making any hypothetical visitor instantly pressed flat. Even though these planets may orbit stably for a long time, their dance can be precarious. Over very long periods, tidal forces can cause the orbit to decay, slowly spiraling the planet toward its star. If enough time passes, a hot Jupiter could eventually fall into its star in a final fiery embrace. This would be a dramatic ending, a final grand ignition, but it highlights how tightly gravity binds these worlds, a constant tug that can never truly be let go. One can even wonder if such a planet could have moons. If 51 Pegasi b had any natural satellites, they would also feel these extremes. A moon orbiting so close to a star would be scorched by the giant planet's glare and by the star's intense heat. It seems unlikely that any small companion could survive long under such conditions. So far, we have no evidence of moons or rings around these giants, but it remains an intriguing possibility to explore. The question of moons or rings reminds us that wherever planets exist, more secrets may lie hidden. Perhaps rings of dust or small remnants could still be discovered around these fiery giants. Some star systems hosting hot Jupiters also have other, more distant planets. Astronomers have found cases where a hot Jupiter shares its system with other worlds orbiting farther out. In those systems, the presence of one world so close to its star hints that a complex gravitational dance shaped the whole system. Perhaps unseen ice giants or rocky planets lurk in the shadows far from the star, waiting to be discovered. In fact, the interactions between a hot Jupiter and any other planets could help explain how it migrated inward. The gravitational interplay within the system might have shepherded the giant inward. Astronomy is a game of clues, and each system with multiple planets teaches us a bit more. Living so close to a star means living in constant, merciless heat. Hot Jupiters feel their star's full inferno every moment. The side of the planet facing 51 Pegasi b basks in an unending blaze. Imagine a world where the sky is a raging furnace and the very air feels like it might ignite. It is a world of perpetual day, with the sun dominating the sky like a second sun. To an observer on the day side, the star would appear many times brighter and larger than our sun does from Earth. It would dominate the sky, a blaze of white light. Temperatures on these worlds soar to extremes beyond anything in our own solar system, often well over 1,000 degrees Celsius. These are temperatures at which the thermal glow of incandescent metal would be bright. For example, one such planet, KELT-9b, reaches temperatures around 4,000 Kelvin, nearly 3,700 degrees Celsius, on its day side, which is hotter than some small stars. Even more typical hot Jupiters are in the range of 1,500 to 2,500 Kelvin, 1,200 degrees Celsius to 2,200 degrees Celsius on their day sides. Under such heat, one side of the planet would gleam like a molten ember against the black of space. On the night side, eternal darkness lies in the planet's shadow. But even there, the heat persists. Atmospheric winds whip around these worlds at astonishing speed, carrying blinding daylight into the endless night. Even in permanent night, the atmosphere would glow dimly from the heat brought by the winds. It would not be truly dark on the night side. Models predict winds of thousands of miles per hour, roaring across the planet in a desperate effort to redistribute heat. In such an environment, familiar materials cannot survive. Water or ocean vapors would be immediately boiled away. Instead, clouds on these worlds may be made of silicates or vaporized iron rather than water. These clouds might form shimmering mist of rock or metal high in the sky. The night side may be cooler, but still scorches at 1,000 degrees or more, a kind of dull orange twilight rather than a true cold night. These planets are in a constant state of violent weather, where the concept of a cool night simply does not exist. No life as we know it could exist there. The conditions are just too extreme and unrelenting. With winds rushing thousands of miles per hour, the weather on hot Jupiters would be extreme indeed. We can imagine fierce lightning storms arising from those silicate clouds, though not of water, but of molten rock or vaporized metals. In those skies, a lightning bolt might flash with the glow of iron, or thunder through an atmosphere of elements we rarely see on Earth. One could imagine the dark sky lit by brief flashes, momentarily illuminating flying shards of glass or stone in the atmosphere. It is a wild picture, but it may not be far from the truth for these turbulent giants. The star's voracious radiation can even erode a hot Jupiter's atmosphere. In the most extreme cases, the planet slowly loses gas into space, forming a comet-like tail trailing behind it. That tail, made of hydrogen and helium, is a reminder of how ruthless stellar heat can be as it strips away the planet, bit by bit. This is not merely theoretical. A few hot Jupiters have indeed been seen with such tails. These worlds are slowly evaporating under the star's breath. Even a planet can gradually be worn down by such relentless conditions. Consider another famous hot Jupiter, WASP-12b. It orbits its star in just over 1 Earth day, making it one of the fastest orbits known. WASP-12b is also being boiled off. Its star's gravity and heat are stripping away its atmosphere at a tremendous rate. In some ways, it's like watching a planet slowly evaporate before your eyes. Another scorching example is WASP-121b, so hot that astronomers discovered a high-altitude layer called a stratosphere. In its case, the upper atmosphere is even hotter than the lower parts. This causes some molecules to emit bright light, like a celestial neon sign glowing in the sky. Finding these hidden worlds took real ingenuity. Astronomers had to become cosmic detectives, inventing clever techniques to reveal what could not be seen directly. Each method is like a tool for listening or watching in the darkness. They learn to listen to the star's subtle heartbeat and to watch for faint shadows crossing the light. One method is to watch for a star's subtle wobble. If a star has a massive planet tugging on it, the star will dance gently. In practice, this wobble can be seen by observing the star's light spectrum. The star shifts slightly toward blue and red as it moves. Mayer and Queloz used this Doppler method to discover 51 Pegasi b. They saw 51 Pegasi move a few kilometers per second toward Earth and then away, on a cycle of every 4.2 days. Each 4.2-day wobble meant the planet circled again, like the steady ticking of a cosmic clock. Those tiny shifts in the star's light told the story of a planet hidden from view. In a sense, they were listening for a slow, distant heartbeat in the light. Another powerful technique is the transit method. Astronomers watch for tiny dips in starlight that occur when a planet crosses in front of its star. It's akin to watching a moth flutter across a distant porch light and noticing the light briefly fade. Telescopes would stare at dozens of stars for hours on end, waiting for a glimpse of a planet. For hot Jupiters, this happens quite often because their orbits are so short. Missions like NASA's Kepler and TESS have watched thousands of stars, catching many hot Jupiters when they transit. Each dip in light tells us the planet's size and orbital period. Hot Jupiters, being large and fast orbiting, make especially strong and frequent signals in transit surveys. Because hot Jupiters make frequent, strong signals, they became the low-hanging fruit of exoplanet hunting. This surprised many and kept discoveries coming year after year. Astronomers have even gone so far as to try detecting these planets by their own light or heat. Space telescopes like Spitzer and Hubble have observed some hot Jupiters in infrared, picking up the planet's thermal glow as it orbits. In effect, these are heat maps of the planet. A few also reflect a faint shine of their star's light, which clever astronomers have teased out. These methods are at the cutting edge of observational astronomy. They show how far technology has come. From barely seeing the star, we now catch whispers of light from its planets. In fact, modern telescopes have even captured faint reflections of starlight from hot Jupiters, as if the planets shine like distant moons in space. Such observations let us measure the planet's dayside brightness and even winds. In the decades since 51 Pegasi b's discovery, these methods have unveiled hundreds of similar worlds. Ground-based surveys like SuperWASP and HatNet have scanned countless stars for the telltale wobble or transit signals. Space telescopes like Kepler and TESS watch thousands of stars at once for even the faintest wink of a planet crossing. Every little blip of light and every slight stellar wobble is carefully logged and examined. In small observatories and large, teams created automated surveys, letting computers flag any suspicious dip or wobble. Hundreds of scientists now pore over this data night and day. Each technique is like teaching the stars to whisper their secrets. As our instruments have improved, new hot Jupiters continue to be found. They were never the most common planets, but they were the first we found because their signals are so strong. Each discovery, each gentle hint from the stars, adds a new chapter to the universe's story. Each time a new planet is added to the catalogue, we revise our understanding of the galaxy a little more. Today, thanks to the methods developed around that first discovery, astronomers have confirmed thousands of exoplanets. Hot Jupiters are only a fraction of this menagerie, but they were the first to arrive in our catalogue. Even amateur astronomers with decent equipment have found a few hot Jupiters by meticulously scanning the skies. As of 2025, astronomers have catalogued over 300 confirmed hot Jupiters, and many more candidates await confirmation. Each one has unique quirks, sizes that can differ by tens of percent, reflectiveness ranging from nearly invisible to surprisingly bright. By studying all these together, we start to see patterns and new puzzles. Finding these worlds truly was like listening to the cosmos. Astronomers had to become patient, attentive listeners and watchers. Each little signal was a clue. Sometimes discoveries were first suspected by one method and confirmed by another, as if multiple instruments were corroborating the same whisper. New instruments are still improving this journey. Missions like the James Webb Space Telescope will study the atmospheres of these giant planets in detail, searching for clues about clouds, chemistry, and winds. New ground-based observatories will push the limits even further. In coming years, new instruments may even catch glimpses of smaller, temperate planets. But until then, hot Jupiters remain a captivating first chapter in exoplanet science, reminding us that nature often surprises even the most careful scientists. For now, our journey among these blazing giants continues, and the night sky remains full of promises. As each new telescope comes online, who knows what wonders our universe will reveal next? The cosmos holds countless secrets, and we have only just begun to uncover them. The heat is unimaginable. All a world like this knows is blistering fire. Picture a planet so close to its sun that the skies are thousands of degrees Celsius. In such an atmosphere of fire, molecules cannot stay intact. Hydrogen, carbon, oxygen, and even metal atoms break apart under the searing heat. Lightning-fast winds howl across the exoplanet, carrying scorching gases at speeds of thousands of miles per hour. These raging winds race from the blazing day side toward the dark night side. On the day side, a fixed hotspot becomes an inferno, a furnace of chemical reactions. At these extremes, even light molecules break down and reform constantly in the air. Astronomers have observed streams of metal atoms like iron being carried by those supersonic winds on ultra-hot planets. The metal vapor is caught up in high-speed jets that slam into cooler regions, mixing gases of different composition in wild ways. The sky can actually blaze with emissions from exotic elements. Sodium, magnesium, and iron glow in the spectra like neon signs in a cosmic city. This fiery theater turns the whole sky into a kaleidoscope of chemical light. This extreme weather is fueled by constant stellar radiation. One side of the planet is locked in endless day, the other side in eternal night. The planet always shows the same face to its star, so daylight falls on one hemisphere without pause. Temperatures soar on the starlit side, creating a giant pressure that drives air toward the shadowed side. When the gas flows into the dark hemisphere, molecules recombine and the cool night prevails. Those winds and chemistry set up a continuous global circulation beyond anything found in our own solar system. These winds can become truly supersonic. On some ultra-hot Jupiters, the jet streams exceed the speed of sound in their hydrogen atmospheres. For example, observations suggest that the winds on WASP 121b reach over 11,000 miles per hour. Such ferocious streams can create shock fronts where gases collide, potentially lighting up parts of the atmosphere in waves of heated air. In effect, the whole atmosphere roars like a high-speed hurricane, redistributing heat around the globe in hours instead of days, instead of Earth-like time. Models show that this vigorous mixing can inject energy deep into the atmosphere, spreading heat far below the visible clouds. A recent dramatic observation highlights how extreme these skies can be. Astronomers watching WASP 76b saw iron vapor streaming off its dayside. There, the temperature reaches around 2,400 degrees Celsius, so iron itself vaporizes. Fierce winds then carry that iron gas to the night side, where it cools and condenses like rain. Daylight on WASP 76b literally boils iron into vapor, which then falls out of the sky on the far side. In essence, this world has a ferocious iron cycle, a storm of fire and metal that truly lives up to its name as a realm of fire. Astronomers have even measured the speed of these winds. By observing tiny shifts in the wavelength of spectral lines during transit, researchers can deduce how fast gases move across the planet. These Doppler signatures indicate jet streams of several kilometers per second, thousands of miles per hour, carrying atoms from day to night. Another intriguing finding is that the hottest point on some hot Jupiters is shifted eastward of the substellar point. In other words, the peak temperature is not exactly where the star is overhead, but carried downstream by the winds. This suggests a strong eastward equatorial jet that transports heat around the globe. The degree of shift varies from planet to planet. On some extremely hot ones, the heat peak is nearly at the substellar point, implying less efficient transport. The physics at play is extraordinary. At temperatures above about 2,000 degrees Celsius, many common molecules like water or methane break apart into simpler atoms. Hydrogen itself begins to dissociate into atomic hydrogen, a process which absorbs a great deal of energy. This dissociation provides a kind of thermostat for the atmosphere, absorbing heat on the day side and releasing it as the atoms recombine on the night side. At even higher altitudes, the atmosphere can become partially ionized. Charged particles then interact strongly with magnetic fields. This can create a hot, electrically conducting layer, a kind of plasma ionosphere or thermosphere, where stellar particles and fields play a role. In some ultra-hot cases, the upper atmosphere can reach temperatures of several thousand degrees, glowing in ultraviolet and even X-rays. Essentially, the terminator region could host an auroral-like ring where charged particles cascade along the boundary of endless day and night. Chemically, this is a wild environment. Species such as titanium oxide, TiO, and vanadium oxide, VO, might remain in gas form and absorb stellar light, creating a stratospheric layer that inverts the temperature profile. Such a stratosphere was actually inferred in the ultra-hot WASP-121b by Hubble observations. On cooler hot Jupiters, TiO/VO would condense out, so each planet shows its own chemistry, depending on temperature and pressure. All of these factors mean weather on a hot Jupiter bears little resemblance to Earth's. The very notions of rain, lightning, or wind must be reinterpreted. Instead of water rain, you might have glass or metal rain, and instead of thunderstorms, we might have magnetic storms. The terminology of Earth's weather fails here, but one can say the atmosphere is supremely dynamic. In summary, the atmospheres of fire on hot Jupiters are defined by extreme heat, extreme speeds, and extreme chemistry. Each of these aspects pushes the boundaries of what we know, challenging our models and offering a view of physics in its most intense form. If one could travel over a hot Jupiter, the experience would be utterly alien. Imagine standing on the limb between day and night. On one side, the star hangs fixed in the sky, an eternally blazing sun, while on the other side, the sky is filled with distant stars and the endless black of deep space. There is no sunrise or sunset here. The sky does not change color with time. Instead, each location on the day side feels perpetual noon, and each on the night side perpetual midnight. In effect, time on a hot Jupiter is frozen in a weird way. A spot just north of the equator will always rotate in the same direction, experiencing the same continuous heating from the star. Because the planet is locked, its rotation period equals its orbital period. Many hot Jupiters complete a spin in just a day or two. Even so, the rotation rate influences weather. A faster rotation can support stronger equatorial jets and Coriolis forces. General circulation models of these planets predict something like a single broad jet stream at the equator, sometimes reaching supersonic speeds, and weaker flows at mid and high latitudes. On our Jupiter, strong eastward super-rotating jets encircle the planet. On a hot Jupiter, one might similarly expect a dominant eastward jet, carried by the blazing heating pattern. The jet redistributes heat, carrying the hottest region east of the substellar point and giving the planet an asymmetric temperature distribution. Observationally, we have some evidence of these wind patterns. High-resolution spectroscopy has caught Doppler shifts in the light of some hot Jupiters, indicating gas streaming from the hot side to the cold side. For example, the carbon monoxide lines in the atmosphere of one hot Jupiter showed a blue shift, implying winds of 2 or more kilometers per second blowing toward us from the approaching limb of the planet. This matches the expected day-to-night motion in a super-rotating wind. So not only are these winds immensely fast, but we are actually measuring them directly from across interstellar space. The chemistry and physics at these extremes are still being sorted out. With no water clouds to give us rainbows or lightning visible as on Earth, The atmosphere's dynamics are driven by basic physics. The flying winds and swirling gases set up planetary-scale waves and instabilities that can only be described by complex, three-dimensional models. Some theorists propose that hot Jupiters might have analogues of Earth's jet stream meanders or even polar vortices, but observed variability so far appears relatively stable. It is conceivable that massive storms could exist, but their signatures are subtle. One curious question is whether any phenomena similar to Earth's weather might occur. If liquid iron or silicate droplets form clouds, raindrops colliding could separate charge and produce lightning. Some models even suggest the strong winds themselves could generate static electricity. If lightning did flash in an iron cloud, it might create brief glints of visible light or drive chemical reactions. So far, no one has seen these flashes, but future instruments might one day catch a spark. In essence, the atmospheres of fire on hot Jupiters are defined by extreme heat, extreme speeds, and extreme chemistry. These factors mean weather on a hot Jupiter bears little resemblance to anything on Earth. They challenge our understanding, showing us physics in its most intense form. If you scale up atmospheric pressure and temperature, you get a system that still obeys physics, but in an alien realm. Hot Jupiters are more than curiosities. They are cosmic laboratories for atmospheric science. Studying them is like examining planet-wide wind tunnels powered by stars. By comparing the data to models, scientists refine the physics of hot gases, learn about hydrogen's behavior at thousands of Kelvin, and even test electrical conduction under these conditions. Each hot Jupiter reminds us that given enough energy, even a gas giant becomes a roiling sea of storms, pushing nature to its limits. High in the skies of a hot Jupiter, clouds form, but not of water or ammonia like on Earth. Instead, they are made of molten rock and metal. Imagine clouds of liquid iron drifting in the gloom, or droplets of silica swirling like glass beads in the wind. On some of these blistering worlds, the night side cools enough for vaporized rock or iron to condense into clouds. This incredible process creates layers of cloud far above what we see in our solar system, turning the sky into a haze of mineral droplets. A surprising discovery came when the James Webb Space Telescope found tiny quartz crystals in the atmosphere of a hot Jupiter called WASP-17b. These particles are essentially bits of glass made of silicon and oxygen. Webb's infrared eyes detected a signature of silica at about 8.6 microns. Quartz like this cannot be lifted from a solid surface. It must form in the sky itself. At around 1500 degrees Celsius, silicon and oxygen in the gas phase combine directly into solid glass particles. The result is a high-altitude haze of glittering crystals, each so small, on the order of nanometers, that they flow on currents like smoke. Another world, WASP-121b, has clouds even stranger than glass. In a study using Hubble and Spitzer, researchers found evidence that its day side is hot enough to break apart water, but its night side is cool enough to rebuild it. They proposed a cycle where hydrogen and oxygen atoms form on the night side and recombine into water vapor, which is then carried by winds back to the day side to evaporate. Meanwhile, the cooling night side also allows metals to condense. Iron, aluminum, and other metal droplets are thought to form clouds up there, possibly even raining precious gems like rubies and sapphires. One model suggests that WASP-121b's night could literally see liquid rocks falling from the sky. Some hot Jupiters famously rain glass sideways. Take HD 189733b. It's an exoplanet so hot and windy that silicate clouds condense into molten glass. Winds of 5,000 miles per hour then carry this glass around the planet. It's been said that this world literally has 5,000 mile per hour glass rainstorms. We can imagine the night sky streaked with fiery sparks as molten glass is whipped sideways by hurricane winds, a spectacle beyond any storm on Earth. These exotic clouds are made of materials we normally see only as solid rocks. Instead of water droplets, these planets have clouds of things like corundum, aluminum oxide, or iron. If you could stand on one of these hot Jupiters with suitable gear, you might watch rubies and sapphires float in the sky. The variety is astonishing. One hot Jupiter might have clouds of titanium oxide and silicates. Another might be cloaked in iron or in statite. Each world has its own cocktail of exotic clouds, with compositions that depend on its temperature and chemistry. These clouds not only create breathtaking weather, but also affect how the planets reflect and emit light, making some appear unusually dark or bright when we observe them. In practical terms, clouds make it tricky to study these atmospheres. A thick cloud layer can block light from deeper down, muting or erasing the spectral fingerprints of gases. Astronomers have seen this effect. Some hot Jupiters exhibit nearly featureless spectra in transmission, which suggests an opaque haze or cloud deck high in their atmospheres. For example, WASP-12b and WASP-43b both appear relatively dark in visible light, likely because clouds of soot-like carbon or silicates absorb much of the starlight. In the infrared, clouds can also add thermal insulation, trapping heat. This means a cloudy night side might stay warmer than expected, while a clear day side could radiate its heat away more efficiently. Clouds on these planets may not be uniform. Some studies find that the day-night terminators can differ in cloud coverage. It is possible that the side at dawn, the evening terminator, is clearer than the side at dusk, the morning terminator, or vice versa. This could be due to winds transporting clouds preferentially or differences in chemistry. We also wonder if these clouds could spark electrical storms. On Earth, clouds can generate lightning through charge separation. On hot Jupiters, raindrops of molten glass or metal colliding might also separate charge, potentially causing spectacular lightning discharges. If such lightning occurs, it could create exotic chemistry, producing nitrides or other compounds high in the atmosphere. Weather on these worlds could be dramatic. The global circulation might lead to ferocious storms, with clouds forming and dissipating as they are carried around the planet. Imagine a storm of iron hail on the night side that evaporates on the day side. So far, we have no direct evidence of lightning or such storms, but the ingredients seem to be there. Clouds in these atmospheres act as a kind of thermostat. They reflect some starlight and absorb some thermal emission, affecting energy balance. Depending on where they form, they can either heat or cool a layer. On Earth, high clouds can warm the surface by trapping infrared. On hot Jupiters, the balance is complex. Dayside clouds might reflect starlight, cooling the atmosphere, whereas nightside clouds trap heat, keeping it warm. Some models show that a highly reflective dayside cloud could significantly cool the day hemisphere, while a thick nightside cloud would maintain warmth. These clouds moderate the extreme temperatures, in effect making the difference between scorch and frigid less stark than it could be. In fact, clouds can even cause temperature inversions. If a high layer of cloud absorbs visible starlight, it heats up the top atmosphere above cooler layers beneath, flipping the usual drop of temperature with altitude into a rise. Observations hint that some hot Jupiters do have such inversions, as discussed earlier with titanium/vanadium oxides. Clouds of similar composition might contribute to that heating. We also consider exotic possibilities. Could clouds spark lightning? If charged particles separate during collisions, large electrostatic forces could build up. On one hand, lightning on Jupiter is driven by water and ammonia. On a hot Jupiter, metal or silicate clouds might play a similar role. Such lightning would be of molten rock, quite unlike Earth's, but it could illuminate the sky briefly and drive exotic chemistry. So far, we've not seen such lightning, but future missions with fast sampling might catch a flicker. Laboratory experiments are being done to simulate these clouds. Scientists heat gases with the same composition as a hot Jupiter's atmosphere to see what condenses. They have produced tiny grains of silicon, aluminum oxide, and iron. These lab results feed into computer models of cloud formation and help interpret telescope data. We have much to learn about cloud physics here. Laboratory experiments and modeling are ongoing to understand these clouds. Scientists have already created high-temperature condensates in the lab, and computer models are advancing, with future observations, for example, measuring how polarization of starlight changes with the planet's phase. We might learn about the cloud particle distribution. For now, we know clouds are there, even if we can't see them directly. They veil the planets in a mineral mist that shapes both their climate and what we observe. In short, clouds on hot Jupiters are exotic but crucial. They shape the appearance and climate of these worlds, turning the haze into an active player in atmospheric dynamics. Even as we can't directly see them, their influence is written in the light that reaches our telescopes. Infrared light gives us a new way to study hot Jupiters. These planets glow in thermal infrared, and telescopes capture that glow across their full orbits. By measuring the changing infrared brightness as the planet circles its star, astronomers can map the temperature across its surface. In a sense, an infrared phase curve acts like a weather map of the planet, revealing how hot different regions are. Long before Webb, NASA's Spitzer Space Telescope and Hubble had begun observing thermal emission from hot Jupiters. These pioneers showed that heat can be unevenly distributed. Now Webb's much greater sensitivity and wavelength range is taking this to a new level. For example, NASA's Webb telescope has been used to make detailed brightness maps of worlds like WASP-18b. In that case, a steep drop of about 1,000 degrees Fahrenheit, 550 degrees Celsius, was seen from the substellar point to the terminator. This map also revealed the presence of water vapor in the atmosphere as a clear signal, and it was the first time a planet was mapped in such detail. One of the clearest results came from a complete map of WASP-43b. Observations spanning a full orbit showed its day side at about 1,250 degrees Celsius, while the night side lingered around 600 degrees Celsius. Those measurements were done in the mid-infrared, essentially using Webb as a giant thermometer. The data also revealed that the night side is cloaked in thick clouds of exotic materials, making it darker in thermal emission than it would be if clear. Meanwhile, the day side of WASP-43b appeared relatively clear and bright. Webb even detected water vapor throughout, confirming earlier hints of water from Hubble and Spitzer, and completing the picture of its atmosphere. Infrared spectroscopy has uncovered many atmospheric chemicals in these planets. Hot Jupiter spectra reveal the fingerprints of water, carbon dioxide, carbon monoxide, methane, and even sulfur dioxide, or ammonia in some cases. These molecules show up as patterns of missing light at specific wavelengths, like a cosmic fingerprint. Combined with the temperature maps, this chemical information is reshaping our picture of hot Jupiters. We now know not just how hot and windy they are, but what gases swirl in their skies. The infrared also hints at high-altitude hazes and temperature inversions on some planets, giving clues to their vertical structure. For example, if silicate clouds form high above the main layers, they can cause a rise in temperature aloft. Observations hint that some ultra-hot Jupiters may have such stratospheres caused by exotic absorbers. These infrared insights have given us our most complete glimpses yet into these alien worlds. They highlight how dynamic and diverse hot Jupiters can be. By comparing different planets' maps and spectra, astronomers are beginning to read the atmospheric systems of these giants like weather reports. We can place hot Jupiters in a multi-dimensional climate space. Future telescopes will expand this approach. Proposed missions will survey dozens of exoplanets in the infrared, building an atlas of their climates. One exciting development is that JWST can simultaneously detect multiple molecules. For example, the spectrum of a planet like WASP-107b from 1 to 12 microns showed clear signatures of water, carbon dioxide, carbon monoxide, methane, sulfur dioxide, and even ammonia. It was like getting a chemical laundry list of the atmosphere. Such broadband coverage means we can build comprehensive models of temperature, composition, and cloud structure. Infrared data also probe how energy is absorbed at different depths. Some molecules act as heaters, absorbing starlight high up, and others as coolants, emitting at depth. By comparing models to observed spectra, researchers infer where the energy is deposited. This tells us if a planet has, say, a high-altitude haze that absorbs visible light, or if it is mostly clear, so starlight heats deeper layers. With each new infrared spectrum, surprises appear. Some planets reveal strange chemical abundances or disequilibrium conditions, like WASP-43b, where methane on the night side was absent. Others display unexpected temperature inversions or variations that challenge simple models. One lesson is clear. Hot Jupiters are not uniform glowing spheres, but complex, layered systems. To obtain these insights, astronomers use a combination of techniques. One key method is phase curve observation. The planet's infrared brightness is monitored continuously over an entire orbit. This tells us how much light comes from the day side and the night side at different points, allowing us to construct a rough map of temperature. In a sense, an infrared phase curve acts like a weather map of the planet, revealing how hot different regions are. Another method is the secondary eclipse. By measuring the drop in total infrared light when the planet passes behind the star, we directly measure the dayside emission. These approaches are analogous to how weather satellites and cameras operate, except on worlds light years away. Before JWST, the Hubble Space Telescope's infrared cameras and Spitzer's IR detectors provided the first glimpses. Those early missions detected hints of water in the near IR for a few planets and measured phase curves in select infrared bands. They proved the concept, but lacked the detail we have now. Now Webb's high resolution and broad wavelength coverage allow us to detect multiple molecules at once and see temperature profiles more clearly. For instance, WASP-121b's atmosphere showed signs of a stratosphere under Hubble. Webb has confirmed a strong stratospheric layer caused by vanadium oxide. Another hot Jupiter, WASP-103b, has been studied by Webb and found to have a very hot day side and even a strong carbon monoxide emission feature, hinting at an inverted temperature layer. Infrared phase curves can also reveal variability. If we track the brightness over many orbits, any weather-related changes, like shifting cloud patterns, could show up. So far, most hot Jupiters have been relatively stable in our observations, but continuous monitoring could uncover daily weather changes. One fascinating aspect is retrieval of chemical abundances. By fitting models to the spectra, scientists can estimate how much water, CO2, CO, methane, etc., are present. This can yield the atmospheric carbon to oxygen ratio and metallicity, clues to the planet's formation history and migration. For example, a higher C/O might indicate formation in a carbon-rich region beyond the ice line. Through infrared spectroscopy, we are effectively reading the DNA of these atmospheres. These infrared insights provide our clearest view yet of hot Jupiters. They show us the heat engines, the chemical factories, and the winds of these distant worlds. Each spectrum and map adds to a growing atlas of exoplanet climates. With more observations, astronomers are building an exoplanet climate database, much like meteorology on Earth, but for alien skies. Proposed missions like ARIEL will survey even more hot Jupiters in the infrared, testing general trends. The thermal light we observe is a treasure trove. It reveals how these planets manage heat, what their weather is like, and even hints at their internal properties. As we gather data, we continue to write the atmospheric story of each hot Jupiter, one infrared wavelength at a time. In this way, hot Jupiters become not static spheres, but characters with evolving stories that we are only now learning to read. Scientists once expected other planetary systems to look much like our own. Rocky worlds close to the star, and gas giants far beyond a cold ice line, where volatiles could condense. In that picture, a planet like Jupiter forms only in the chilly outskirts of a disk. When 51 Pegasi b was found in 1995 to be a Jupiter-mass planet orbiting its star in just 4.2 days, it came as a surprise. In fact, 51 Peg b was literally the first extrasolar planet found orbiting a Sun-like star. The radial velocity method used to find it is most sensitive to heavy planets on tight orbits, which explains why the earliest discoveries were dominated by hot Jupiters. This discovery revealed that classic formation models needed revision. In those early days, astronomers even looked back to old ideas for clues. Back in 1952, astronomer Otto Struve speculated that planets the mass of Jupiter could theoretically reside 50 times closer to a star than Earth is to the Sun, though the technology of the time couldn't test the idea. By the 1990s, that vision was still considered highly unlikely. The discovery of 51 Pegasi b forced a rethinking. Within months, theorists began crafting explanations. Doug Lynn, in 1996, proposed that a Jupiter could form far out and then gently spiral inward through the primordial gas disk. His disk migration theory reconciled hot Jupiters with traditional formation, a distant gas giant moving inward as the gas dissipates. For a time, this looked like a neat solution to the puzzle. This quiet migration model made sense. A giant grows to full size while the gas is thick, then glides inward gently. But even as new theories formed, the mystery deepened. Some scientists proposed alternatives. Perhaps hot Jupiters formed right where we see them, in place, building up from supermassive solid cores. Another idea was violent. Interactions with other planets or a distant star could fling a Jupiter into a star-skimming trajectory, and tidal friction would then circularize it. In short, by the late 1990s, three main scenarios had emerged: in situ formation, smooth disk migration, and high eccentricity migration via scattering or Kozai effects. Could hot Jupiters have formed right where they are, in situ? This idea has been considered. In situ formation would require a very large solid core to assemble near the star and then accrete gas. However, classical models show this is very challenging. It would demand an enormously dense concentration of solids, roughly 10 to the power of 4 grams per square centimeter, in the inner disk, far higher than is thought to occur normally. In other words, under typical conditions, it seems impossible to build a Jupiter-sized core so close in. As a result, most researchers view in situ formation as unlikely, except in exceptional cases. A few studies have explored whether migrating super-Earth cores could seed such planets, but generally in situ formation has not been the favoured explanation for hot Jupiters. Even with these ideas in hand, astronomers realised the puzzle would not be trivial. Each hypothesis offered some promise, but also questions. The real situation could even involve all of them to varying degrees. The door was open for a detailed look at the favoured scenarios. One leading theory is the disk migration scenario. In this picture, a Jupiter-mass planet forming beyond the frost line carves a gap in the protoplanetary gas and is carried inward as the disk itself accretes onto the star. This process, known as Type II migration, typically moves the planet on the disk's viscous timescale. Over the few million years the gas remains, a Jupiter-mass world can spiral from several astronomical units down to a tiny orbit. Essentially, the planet rides the gas flow toward the star, explaining a hot Jupiter's close-in location if that migration halts safely. Simulations of Type II migration confirm this general behavior. In fact, a Jupiter-mass planet in a disk like the minimum mass solar nebula is expected to drift inward steadily. Planets just above Saturn's mass open only partial gaps and migrate somewhat faster. But by the time a planet reaches Jupiter mass, the full Type II regime typically applies. Observationally, astronomers have imaged young disks with gaps and rings that may hint at giant planets at work. If such a planet had time to migrate, it may end up as a hot Jupiter. The details depend on the disk. A very viscous disk yields rapid inward motion, whereas a low viscosity disk might stall the planet's drift. In a true Type II migration, the giant's gravitational nudges do not automatically wipe out its siblings. Instead, the planet and any inner bodies settle into a stable configuration. Migration is relatively smooth. The planet maintains roughly the disk's plane, and its orbit remains nearly circular. The result is usually a nearly circular orbit by the time the gas disappears. This means we would expect some hot Jupiters to have retained smaller inner companions, at least in the simplest picture. Yet there was a snag. Observationally, many hot Jupiter systems turned out to have no nearby planetary companions. Surveys like Kepler found that hot Jupiters often orbit alone. This absence was unexpected if migration were gentle. One expert summary noted that standard disk migration cannot easily explain why hot Jupiters so often lack neighbours. That suggestion opened the door to alternative theories, which we will explore next. For the more violent paths, imagine giant planets interacting chaotically after the disk has gone. Their orbits can become unstable, leading to close encounters and gravitational slingshots. One possible outcome is that one planet is sent onto a highly elongated, eccentric path, with its periastron diving near the star. Each close passage delivers a tidal kick. Strong tides on the star and planet drain energy and shrink the orbit. Over time, this process, called high eccentricity migration, transforms an initially elongated orbit into a tight, circular one. The journey is wild and disruptive, perfect for the term violent pathway. One variant of this chaotic picture involves a distant companion on an inclined orbit. In the Kozai-Lidov scenario, a companion perturbs the hot Jupiter's orbit, exchanging inclination and eccentricity. The planet can be tilted and sent onto a very elongated orbit. When its perihelion dips near the star, tides take over and circularize it in place. This process can produce hot Jupiters with highly inclined or even retrograde orbits. In fact, roughly half of known hot Jupiters have distant Jupiter mass or larger companions, consistent with this kind of gravitational perturbation. Simulations of chaotic migration support these ideas. If a Jupiter mass planet is flung inward, it tends to clear out its interior. In one study, either the inner planets were sent into the star or ejected, or the migrating Jupiter itself was ejected. But rarely did multiple worlds survive. Astrobites summarizes this as, "A giant migrating inward will get rid of any other tight orbit planets." This matches the observations. Most hot Jupiters are indeed found alone. Once a gas giant is delivered very close to its star, whether by disk migration or by scattering, tidal forces take the reins on its final journey. The mutual gravity raises tidal bulges on each world. If the star rotates more slowly than the planet orbits, the bulge lags behind and acts like a brake on the planet's motion. Over time, energy is dissipated and the orbit slowly shrinks. Similarly, any orbital eccentricity is eroded as tides pull the orbit rounder with each close passage. The end result is a nearly circular orbit. Typically, this parking orbit is only a few stellar radii out, and it can be remarkably stable. Models indicate that after settling, further decay is negligible on billion-year timescales for Sun-like stars. During this time, the planet also becomes tidally locked. One face always points to the star. As a result, one hemisphere broils in perpetual day and the other in perpetual night. Tidal locking and heating often have profound effects on the planet. A locked hot Jupiter has enormous temperature differences between the day side and night side, driving exotic weather and supersonic winds. The intense tides and stellar irradiation can also puff up the planet's atmosphere, lowering its density. In some cases, this may even push the planet toward its Roche limit. If a hot Jupiter's outer layers extend too far, the star's gravity can strip material off the planet. Nevertheless, for most hot Jupiters, this process only makes them bulgy. They settle into a close orbit and stay there for long times. We also see that most hot Jupiters stop at about a 3-day orbital period, around 0.03 to 0.05 astronomical units. One reason may be torque balance. According to Heller, 2019, when the disk is still present, the inward pull from disk gas can balance the outward push from the star's tidal bulge at roughly 0.05 astronomical units. Planets migrating inside that radius can stall and accumulate there. After the disk vanishes, the star's tides continue to push the planet slightly outward, reinforcing this parking distance. This mechanism can naturally create the observed pile-up of hot Jupiters at a few-day period. Closer to the star, additional barriers appear. The star's magnetic field often truncates the inner disk, creating a cavity at a few stellar radii. A migrating planet would stop at that cavity edge. Also, a planet cannot survive inside its Roche limit, where tidal forces would disintegrate it. For a Jupiter around a Sun-like star, this limit is around 0.01 astronomical unit. We find that very few hot Jupiters exist inside approximately 0.02 astronomical units. Intense stellar irradiation also starts to strip their atmospheres. A hot Jupiter at approximately 0.02 astronomical units would lose roughly 5 to 7% of its mass over a lifetime, and closer in, much more. Over time, this evaporation could turn a gas giant into a barren core, a Chthonian planet, although none has been definitively observed. These effects combine to set a hard inner boundary on where hot Jupiters can survive. Meanwhile, new discoveries have continued to surprise astronomers. The WASP-47 system, for example, is a hot Jupiter with 3 nearby companion planets, 2 smaller ones even inside its orbit. This broke the no neighbours rule and showed that migration can sometimes preserve inner planets. Such exceptions imply that nature may sometimes transport giants inward more gently. On the other hand, many other hot Jupiters remain solitary and often misaligned, suggesting a violent past. This split in the data hints that more than one pathway is at work. Other clues add to the tension. Many hot Jupiters have orbits aligned with their stars, especially around cool stars, while a significant fraction are misaligned or retrograde, again pointing to differing histories. There is also a strong correlation with stellar composition. Metal-rich stars are far more likely to host hot Jupiters. According to one model, this happens because metal-rich disks more readily produce the massive cores or migration traps needed, causing such stars to end up with more hot Jupiters. These trends suggest that the planet's birth environment, its disk's makeup, influences which process dominates. In short, the evidence suggests that nature employs more than one trick to place Jupiters close to their suns. Some hot Jupiters likely came in through the gas disk gently, others were hurled inward in chaotic ways, and perhaps a few even formed locally under special conditions. Theoretical models continue to adapt, combining these scenarios and refining their predictions. Observers are gathering more data, from surveys of young stars, detailed architecture of exoplanet systems, and measurements of stellar obliquity, to untangle this puzzle. Each hot Jupiter studied adds a piece to the picture. We have peeled back several layers of this mystery, but the story is far from over. Our exploration will continue. In the next part of our journey, we will look at new discoveries and open questions as the search for understanding hot Jupiters goes on. Imagine a world so close to its star that its atmosphere is literally boiling off. On some hot Jupiters, the dayside temperature soars into the thousands of degrees. Their skies become cauldrons of atoms rather than molecules. Scientists call these the ultra-hot Jupiters. In fact, astronomers measure Kelt 9b's dayside at around 4,600 Kelvin, over 4,300 degrees Celsius, hotter than many ordinary stars. The amount of energy these planets receive is so extreme that their atmospheres can break down. Under that intense fire, even molecules like hydrogen can split apart, and familiar metals like iron and magnesium can vaporize into the air. These planets do not just have high temperatures, they enter a regime of chemistry more akin to a stellar atmosphere than to any planet we know. These scorching giants earned the nickname hot Jupiters, but star scorcher might be more fitting. For perspective, Jupiter orbits at 5.2 astronomical units from the Sun. Some hot Jupiters lie within about 0.02 astronomical units of their star, roughly 3 million kilometers, or only 1/50th the Earth-Sun distance. At that proximity, a hot Jupiter would be blasted by an unimaginable flux of radiation. If Jupiter itself were moved into such a tight orbit, its dayside temperature would exceed 2,000 degrees Celsius, and it would glow almost like a faint star in our sky. This comparison shows how extraordinary hot Jupiters are. Even a slight change in distance makes a huge difference in heating. In fact, many astronomers joke that such planets should not exist. According to older models, Gas giants simply shouldn't be able to form or survive so close to a star, yet these worlds are very real. How do we know their temperatures? Astronomers use clever tricks. One method is infrared eclipse measurements. When a transiting hot Jupiter passes behind its star, a secondary eclipse, the combined light dips by a tiny amount. That dip reveals the planet's own glow. By observing at multiple wavelengths, scientists can infer the planet's temperature map. Using this technique, they found Kelt 9b's day side is about 4,600 Kelvin. Even on the night side, hidden from the star, Kelt 9b stays over 2,600 degrees Celsius. That indicates an incredibly hot world, even in the dark. Imagine standing on such a planet. The star would dominate the sky, never setting, always a brilliant, burning disk. The day side might be so bright and hot that most complex molecules cannot survive. The atmosphere there would be a boiling soup of atoms and ions. If you could wander to the planet's terminator, the line between day and night, you'd find a sharp boundary between blinding light and near darkness. Even on the night side, with the star gone, the sky would still glow a deep red from residual heat. In that alien sky, the familiar cycle of sunrise and sunset would disappear. One horizon would blaze with eternal noon, and the other would be eternally dusky. The usual concept of day and night dissolves on such a world. Because of these extremes, hot Jupiters blur the line between planets and stars. If KELT 9b were floating freely through space, its temperature would qualify it as a brown dwarf by some definitions. It's that hot. But since it orbits a star, we still call it a planet. And its host star is special too. KELT 9, for example, is an A-type star around 10,000 Kelvin, much hotter than our Sun. That star bathes the planet in intense ultraviolet and even X-ray radiation. So KELT 9b gets not only tremendous heat, but also a barrage of energetic photons that continuously break apart its atmospheric molecules. In many ways, ultra-hot Jupiters act like laboratories for extreme physics. By studying them, scientists learn how molecules survive or shatter under the harshest conditions imaginable. Every new discovery of an ultra-hot Jupiter feels like an achievement. WASP-33b, found in 2010, was one of the first extreme cases. It orbits a star more than twice as hot as the Sun. In 2017, the Mascara survey, also called Kelt 20, found another, Mascara 2b, with a day side around 2,500 degrees Celsius. That same year, Kelt 9b was found and immediately set a new record as the hottest. Then NASA's TESS mission found planets like TOI 1431b with dayside temperatures near 2,700 degrees Celsius. Each new find redefines the limits of planetary conditions. Every time astronomers search the sky, they uncover another blazing world, teaching us that planets can exist in even more extreme environments than we once imagined. The very existence of these searing worlds surprised theorists. Early models suggested that gas giants could not form so near a star. Instead, we now believe hot Jupiters form far out and migrate inward. The discovery of the hottest examples, even closer than thought possible, forced scientists to rethink their models. It raised new questions. Were these planets pushed inward by other massive bodies? Did they migrate smoothly through the protoplanetary disk? Or did chaotic events fling them inward? Ultimately, each finding helps refine our story of how planets move and evolve. In fact, the heat itself sets up interesting phenomena. On these planets, some of the energy on the day side goes into breaking molecules like hydrogen. That process actually absorbs heat, meaning the daytime air isn't as hot as it could be. Later, as hydrogen atoms recombine into molecules on the night side, they release heat there. This cycle of dissociation and recombination partially redistributes heat around the planet, reducing the day-night contrast. For example, KELT-9b's night side being only approximately 2,600 degrees Celsius implies strong winds or chemical processes are moving heat to the dark side. Because these planets are so puffy and low in density, their own gravity barely holds on to the atmosphere. Many hot Jupiters are significantly inflated, much larger than expected. The intense stellar radiation and other processes heat their insides. One idea is that strong winds in a hot Jupiter's magnetic field generate electric currents, ohmic heating, depositing extra heat deep in the planet. Another is that the tidal forces themselves flex and heat the interior. Whatever the cause, the result is that the planet's radius swells. A Jupiter in such a furnace can become tens of % larger. This makes them easier to detect, larger silhouette, but also more fragile under tidal strain. The hottest hot Jupiters push our definitions. They begin to resemble stars in some ways, yet they remain planets. Each one is a unique laboratory for extreme physics and chemistry. Studying them teaches us about atmospheric processes under conditions impossible on Earth. The searing day side of KELT-9b is nearly as hot as a small star, and its night side still glows at several thousand degrees. In fact, some hot Jupiters shine almost like mini-stars themselves. Only true stars are much hotter. These planets sit at the border between planet and star. Their existence expands our understanding of what a planet can be. Hot Jupiters at 0.02 astronomical units orbit only about 3 million kilometers from their star. That distance is about 1/50th of the Earth-Sun distance, a cosmic hair's breadth. At that separation, these giants feel gravitational and radiative forces unlike anything in our solar system. It's as if they reside in a stellar furnace. Such proximity underscores their extremeness. Even moving Jupiter that small distance inward would cook its atmosphere away. These cosmic infernos show us how violent and varied planetary systems can be. These hot Jupiters cannot possibly be habitable by any earthly measure, of course. And yet, by studying these fiery giants, we gain insight into the processes that shape all planetary systems, even our own. In many ways, they are natural laboratories. They push physics and chemistry to the edge. The more we learn about hot Jupiters, the more we understand the range of possible worlds in the universe. Beyond blazing temperatures, many hot Jupiters behave strangely in their orbits. Unlike the neatly aligned planets of our solar system, these distant giants often orbit at odd angles. Some even swing around their stars in reverse. Imagine a planet moving the opposite way of its star's rotation. If you could stand on it, the sun would rise in the west and set in the east. These tilted orbits hint at dramatic histories. The most famous case is WASP-17b, discovered in 2009. It is one of the puffiest known, roughly twice Jupiter's radius, and it orbits backward. When astronomers first measured its orbit angle, they were stunned. It was literally going the wrong way. Another is HATP-7b, found in 2008, which Kepler studied extensively. Kepler's data let scientists map its dayside and revealed that HATP-7b's orbital plane is tilted by nearly 180 degrees compared to its star's spin axis. These discoveries were shocks, suggesting something violent happened to send these planets on such tilted paths. Astronomers can measure these spin-orbit angles during a transit. As a planet crosses its star, it blocks the blue-shifted or red-shifted part of the rotating star sequentially. This Rossiter-McLaughlin effect lets us infer the orbit's tilt. Using this technique, dozens of hot Jupiters have been examined. A curious pattern emerged. Those orbiting very hot, massive stars often have large misalignments, while those around cooler stars are mostly aligned. This suggests that the star's properties matter. Cooler stars with deep convective zones might realign over time, whereas hotter stars do not. The details are still under study, but the data hint that stellar structure and tides play a role in setting the final angle. These odd orbits give clues about the planet's pasts. They suggest that many hot Jupiters did not quietly form in place. Instead, they likely formed farther out and were thrown inward by violent encounters. One idea is planet-planet scattering. Imagine two giant planets on a collision course, exchanging energy and hurling one inward. Another is the Kozai mechanism, where a distant companion, star or planet, tugs gravitationally to flip the inner planet's orbit. Either process can tilt an orbit dramatically. In some systems, we actually see such distant companions, supporting these theories. Another possibility is that the star itself tilted early on. If the star's rotation axis moved, a planet could remain in the original disk plane and still appear misaligned. However, this seems less common. Contrast all this with our solar system, where the planets and the sun's equator all lie neatly in one plane. That orderly arrangement highlights how chaotic hot Jupiter systems can be. Our planets orbit within a few degrees of the sun's equator. The hot Jupiter misalignments show that nature need not follow our solar system's rules. In fact, a significant fraction of known hot Jupiters, roughly a third or more, have large orbital tilts or even retrograde motion. This means they're not just isolated oddballs. Each new system studied often yields yet another tilted orbit. Every such discovery is a reminder that the cosmos can rearrange orbits in dramatic ways, and that our expectations must remain flexible. The variety of these tilted orbits is like watching a cosmic game of billiards. One close encounter can send a planet spinning off at an odd angle, much like knocking a cue ball sideways. In multi-planet systems, interactions can flip an orbit by tens of degrees. Each such event reshapes the system's architecture. Observing this orbital diversity shows that the processes forming planetary systems can be as chaotic as they are orderly. Indeed, a retrograde hot Jupiter behaves in a way more bizarre than anything in our solar system. It reminds us that the universe is under no obligation to follow our intuitions. Each unusual orbit is a surprise that challenges those expectations and makes the study of hot Jupiters endlessly fascinating. Some of these wayward gas giants also orbit their stars so closely that they are on the brink of destruction. Physicists call the boundary where a planet begins to tear apart the Roche limit. If a planet crosses that boundary, stellar tides can overcome the planet's gravity. The result can be spectacular. The planet's shape distorts into an egg-like form, and its atmosphere can pour off into space. At worst, a hot Jupiter might lose so much mass that it leaves only a core behind. In effect, these planets are on cosmic scenic death marches. One vivid example is NGTS 10b, discovered in 2019. It completes an orbit in just 18.4 hours. Its closeness to its star means it is nearly at its Roche limit. Models predict that in just a few tens of millions of years, a blink of an eye astronomically, NGTS 10b will start to fall apart. Another famous case is WASP 12b, which orbits in 26 hours. Observations show WASP-12b is not only heated to about 2,500 degrees Celsius, but is actually spilling gas onto its star. Telescopes have seen a faint, comet-like tail of material trailing the planet. In these systems, the planet and star engage in a furious exchange. The star tugs gas away, while the planet still holds on for now. Heat and gravity together can bloat a hot Jupiter even more. Many hot Jupiters are inflated, meaning they have much larger radii than expected. The intense stellar heating and tidal forces deposit extra energy, puffing up the planet. For a very hot, low-density gas giant, even a small additional force can expand it further. A theory called ohmic heating proposes that star-driven winds and magnetic fields induce currents that heat the interior. Whatever the mechanism, the outcome is that many hot Jupiters become swollen, some almost twice Jupiter's normal size. This inflation increases their surface area, exposing them even more to the star's grip, and raising the chance that they will cross the Roche limit. The effects of tides go beyond shape. Close-in planets and their stars exert tidal forces on each other. While the star pulls on the planet also raises tidal bulges on the star's surface. In extreme cases, this can affect the star's rotation or activity. For example, WASP-18b is about 10 times Jupiter's mass, orbiting in just 22.6 hours. Some scientists suggest that such a massive planet, so close, could be spinning its star up a bit or stirring stellar activity. These effects are subtle, but they highlight that the star and planet can influence each other in both directions. Over long times, tidal forces also shrink the orbit. A close hot Jupiter is slowly losing orbital energy to its star. Observers have actually detected evidence for this. In the case of WASP-12b, precise measurements of its transit times show that the transits occur slightly earlier with each passing year. This suggests WASP-12b's orbit is decaying. It is spiraling inward. If this trend continues, WASP-12b will eventually spiral into its star. It's a cosmic slow-motion death spiral, a process that may play out over millions of years. What is the ultimate fate of a hot Jupiter? One possibility is it ends up as a so-called Chthonian planet, the burned-out core of a former gas giant. As the atmosphere is stripped away, a dense rocky or metallic core could be left. Astronomers speculate that some of the very hot, rocky super-Earths we see might actually be the remnants of evaporated giants. By observing hot Jupiters that are actively losing mass, we may one day see a giant planet in the process of vanishing, revealing a new kind of world. Studying these dying planets offers a glimpse at the final act of planetary evolution. Astronomers have even considered whether the stars themselves get polluted by this process. If a planet is shedding gas, some of that material might fall onto the star. Researchers have looked at the spectra of host stars like WASP-12 to see if they contain extra elements, silicon, iron, etc., that could have come from the planet. So far, the evidence is not conclusive, but the idea is intriguing. Not only does the star strip material from the planet, but the planet may in turn seed the star with its own elements. The intense heat and tidal forces have other effects. The most inflation and strongest tides often create strong winds. A hot Jupiter about to break apart will have fierce weather. Computer simulations show winds over 5,000 kilometers per hour can circulate on these planets, transporting heat and shaping their atmospheres. In extreme cases, the temperature difference between day and night can exceed 2,000 degrees Celsius. Yet even these extremes may be moderated by chemistry. When hydrogen atoms on the night side reform H2, they release heat and slightly warm the night side, as we saw. Even the concept of a day changes. On a planet with a 16-hour year, every morning starts again in less time than we take a nap. By the time you go to sleep on such a world, you might have already lived through an entire orbit. In effect, what we call 1 year would span just a few hours there. This extreme speed redefines day and year. It's as if on these worlds, year and day are the same thing, locked together by tidal forces. It's worth noting that planets with orbits measured in hours must remain above a certain size and mass to survive. To date, the shortest period hot Jupiters have orbits around 16 to 18 hours. Even closer in, the tidal forces would simply shred a gas giant. That means we are already seeing nature's limit. The planets racing around in mere hours are skating right on the edge of survival. The moment they fall a bit closer, they would cross the Roche limit and disintegrate. To detect such rapid planets, astronomers rely on continuous monitoring. Telescopes like NASA's TESS stare at large regions of sky for weeks on end. This allows them to catch multiple transits of ultra-fast planets. When the dips in light recur every few hours, it flags an ultra-short orbit. Ground-based surveys can also find these worlds, but only if they can observe continuously through a whole transit. The upshot is that most of our shortest period discoveries have come from telescopes with a long, uninterrupted view of the sky. Imagine standing on one. If survival were possible, you'd see your sun set and rise multiple times in what we call a single night. Morning would become afternoon in hours, and you'd experience dawn and dusk dozens of times per Earth day. The sky would transform from bright to dark and back again at a dizzying pace. Living on such a planet, time would feel completely warped. What we call an hour or a day would not match the rhythms of that world at all. The hearts of these planets are beyond our normal imagination. But we don't need analogies alone. We have measured some of their chemistries directly. When a hot Jupiter transits its star, a tiny bit of starlight filters through its atmosphere, imprinting the signature of the gases. Using telescopes like Hubble, Spitzer, and now the James Webb Space Telescope, JWST, astronomers have identified familiar molecules. Water vapor and carbon monoxide are common findings on hot Jupiters. On cooler hot Jupiters, still around 1000 to 1500 Kelvin, methane, CH4, can appear, though it often disappears under higher heat. Yet alongside these expected molecules, astronomers have found surprises. On WASP-76b, one of the hotter examples, iron vapor literally rains out on the night side. Observers saw iron gas on the morning side of the planet and none on the evening side, as if iron condenses into droplets as the gas cools. In KELT-9b, which is even hotter, molecules hardly exist on the day side. Instead, astronomers detected atomic iron and even ionized metals like titanium, Ti+, in the infrared. In that sky, the familiar chemistry of Earth is replaced by vaporized rock and metal. Hydrogen itself gets torn into protons, and even the hydrogen anion H- becomes important, acting as a kind of transient greenhouse gas. Clouds and hazes add another twist. On some hot Jupiters, astronomers see hints of clouds made of exotic stuff, droplets of molten silicate rock, tiny particles of metal oxides, or perhaps even corundum, the mineral of rubies and sapphires. In cooler examples, clouds of magnesium silicates or iron droplets can form high up. These clouds can mute or flatten the spectral features of lower gases. On other planets, by contrast, the skies appear remarkably clear, letting us see deep into the atmosphere. Figuring out which worlds are cloudy is an ongoing challenge. For example, some intermediate temperature hot Jupiters show signs of high-altitude hazes that scatter blue light, explaining the deep blue color of HD 189733b's sky. Detecting trace molecules is becoming increasingly sophisticated. High-precision spectroscopy has revealed even tiny amounts of some gases. For instance, JWST has already confirmed water vapor in multiple hot Jupiter atmospheres. In 2022, it even detected carbon dioxide, CO2, in the warm gas giant WASP-39b, the first clear CO2 in any exoplanet. While WASP-39b isn't ultra-hot, this milestone shows that JWST can pick up molecules on these worlds. It sets the stage for mapping CO2, CO, and other molecules in truly hot Jupiters very soon. In coming years, we expect Webb and other telescopes to find ammonia, hydrogen sulfide, or other gases that we've only hinted at. Each new molecule adds a new color to the cosmic palette and brings fresh surprises. The intense ultraviolet light from the star also drives exotic chemistry. On the day side, UV photons split molecules into atoms and radicals. These fragments can recombine into unexpected species or form complex hazes of soot-like hydrocarbons. For example, some theorize a form of high-altitude smog may coat the hottest planets, formed by carbon compounds that wouldn't exist on a cooler world. These photochemical products can show up as mysterious absorption or emission features, or even hide other gases from detection. Metal hydrides are another frontier. At the high temperatures of hot Jupiters, molecules like iron hydride, FeH, or chromium hydride, CrH, become stable. These have been observed in the spectra of ultra-cool brown dwarfs and are now being searched for in exoplanets. If present, metal hydrides would contribute distinct infrared absorption bands, providing more insight into temperature and composition. Similarly, astronomers have detected ions of heavy elements, such as calcium plus and iron plus, in the upper atmospheres of the hottest Jupiters. The presence of these ions tells us that the star's UV light is penetrating deeply, ionizing atoms high in the sky. Each hot Jupiter seems to have its own story. One recent study of WASP-76b showed that sodium atoms appear on the day side, but vanish on the night side, implying they condense into something like salt or clouds as the gas cools. Another hot Jupiter, WASP-12b, has shown hints of carbon-rich chemistry at times. The diversity is staggering. Basically, no two hot Jupiters are chemically identical. Every time astronomers observe a new one, they either find familiar gases in new environments or uncover completely unexpected constituents. The atmospheres of these planets hold a brew as exotic as the planets themselves. Some of the most iconic hot Jupiters have become legends in exoplanet science. The very first, 51 Pegasi b, a hot Jupiter not known by that name yet, was discovered in 1995 around a sun-like star 50 light-years away. It's roughly Jupiter's mass, but orbits in just 4 days. Astronomers nicknamed it Bellerophon, after the hero who tamed Pegasus, since 51 Peg is in Pegasus. Its discovery was so revolutionary that the finders won a Nobel Prize in physics. A few years later, HD 209458b, also called Osiris, was found in 1999. It was the first transiting exoplanet ever seen. As it passed in front of its star, astronomers could measure its atmosphere. they detected sodium, and later even signs of hydrogen escaping. These early discoveries showed us how different exoplanets can be, compared to our familiar solar system. Another early celebrity is HD 189733b 2005. This planet amazed scientists by being a deep electric blue in reflected light, unlike Jupiter's yellowish hue. The blue color likely comes from high-altitude silicate hazes in its atmosphere, giving it a sky as blue as Earth's, but for very different reasons. HD 189733b also has some of the fastest winds ever measured. Researchers tracked storms racing around it at a few kilometers per second. In the same era came TAR-ES4b, an extreme case of inflation. TAR-ES4b's diameter is almost twice Jupiter's, making it extremely puffy with very low density. Its discovery highlighted the puzzle of inflated planets. Then there are the WASP planets, which have churned out numerous headlines. WASP-12b, discovered in 2008, is one of the hottest known and orbits in just 26 hours. It glows an orange-red color from the heat and is actually spilling gas onto its star. It may have an evaporating tail. WASP-18b, also found in 2008, is about 10 times Jupiter's mass and completes an orbit in only 22.6 hours. Its heft and proximity make it a likely candidate for orbital decay. Each of these worlds became famous and taught us something new about planetary evaporation, tidal physics, or chemistry. Other examples stand out too. WASP-17b, also discovered in 2009, is famous for being the first found on a retrograde orbit. It is very bloated and whips around in just over 3.7 days. HATP-7b, found in 2008, was intensively studied by Kepler. Kepler's observations allowed scientists to map its dayside and confirmed its orbit is highly tilted, almost polar. It also showed that HATP-7b's hottest spot is shifted eastward by fierce winds, one of the first detailed wind maps of an exoplanet. Each discovery feels like meeting a new character. WASP-17b, the giant backwards world; HATP-7b, the windswept day-night mapped globe, and so on. Some planets have unique claims to fame. TARIS-2b, discovered 2006, earned the title of the darkest known exoplanet. It reflects less than 1% of starlight, making it blacker than coal. If you could see TARIS-2b in reflected light, you wouldn't. It's essentially pitch black. WASP-43b, with an orbit under 20 hours, has become one of the most studied short-period giants. Observations with the Hubble Space Telescope showed its dayside reaches about 1,600 degrees Celsius, while the night side is much cooler, an unprecedented contrast. Studying WASP-43b taught us about heat redistribution in a fast-orbiting world. These famous hot Jupiters are just the beginning. Every year brings new survey discoveries. If a new bright star shows a telltale dimming, a new hot Jupiter is often the result. Each one we find is like a storybook example. The blue planet, the brown dwarf mass planet, the puffy planet, the doomed planet losing mass. They remind us that planetary systems can be wildly different from our own. These iconic giants, Bellerophon, Osiris, the blue planet HD 189733b, the backward spinner WASP-17b, and countless others, form a gallery of extremes. Each one shines a spotlight on the incredible variety of planets in our galaxy. Take WASP-121b as another example. Discovered in 2015, it orbits in just 1.27 days. WASP 121b was one of the first planets where astronomers confirmed a stratosphere, a thermal inversion. In its atmosphere, water shows up in emission rather than absorption. That means the upper layer is hotter than the layers below. This inversion likely comes from molecules like titanium oxide or vanadium oxide absorbing stellar light high up. Finding it was a major proof of concept, confirming theories from decades earlier. The list goes on. Every search project has its hot Jupiter champion. The WASP surveys found dozens of hot Jupiters, including WASP 8b, which orbits in 8 days and is retrograde. The Kepler spacecraft, even though it found mostly smaller planets, still discovered hot Jupiters like Kepler 7b and Kepler 13ab, which revealed odd cloud patterns and brightness variations. Smaller teams contributed too. The EXO survey found EXO 1b, HatNet found HatP 1b and HatP 7b. Each success story added to our roster of familiar worlds. Not all of these giants fit neatly into categories. Some are so massive they blur the line with brown dwarfs. For example, KELT-1b has about 27 times Jupiter's mass. Normally at that mass, we'd call it a brown dwarf, but it orbits in just 1.22 days, like a hot Jupiter. CoRoT-3b is another heavy one at approximately 22 Jupiter masses. These super-Jupiters remind us that nature creates a continuum. Even though we label them differently, the underlying physics is the same. Gravity, radiation, and tides all apply continuously. In summary, the roster of famous hot Jupiters is rich and growing. We have 51 Pegasi b, Bellerophon, HD 209,458b, Osiris, HD 189,733b, The Blue World, WASP-12b and WASP-18b, Stellar Scorchers, WASP-17b, The Retrograde Goliath, and many more. Each one taught us new lessons about planetary extremes, unexpected orientations, bizarre chemistry, and ultimate fates. They are landmarks in our exploration of the cosmos. And still, the universe keeps delivering more. As long as we keep searching the sky, more iconic hot Jupiters will emerge. The story never ends here. There are always more worlds out there, waiting to surprise us even further. And now, we turn our gaze back to the stars themselves. So far, we have explored how these giant planets dwell so close to their blazing suns and the storms that rage on their surfaces. But such enormous planets do not simply orbit passively. They leave subtle fingerprints on their host stars as well. The star's own magnetic field and rotation can be influenced by the presence of a hot Jupiter. We will gently explore how these close-in giants stir their stars through magnetic embraces and gravitational tugs. This interplay is not just theory, it has been seen in practice. For example, the star HD 179949 exhibited extra-chromospheric emission timed exactly with its hot Jupiter's orbit, as if the planet had imprinted a bright spot on the stellar surface. Another star, HD 189733, showed periodic X-ray flares that coincided with its planet's passage across the star's face. These examples hint that the magnetic connection can literally light up parts of the star. In such systems, the planet is like a hidden conductor, activating sections of the star's atmosphere in rhythm with its orbit. Picture a hot Jupiter locked in its tight orbit, its powerful magnetosphere brushing against the star's outer layers. The magnetic fields of planet and star can twist and reconnect, like tangled rubber bands being pulled and released. When these fields reconnect, they can discharge energy into the star's chromosphere, briefly heating and lighting up the star. Astronomers have indeed observed stars glowing brighter in ultraviolet and calcium emissions at exactly the spot facing the planet. It is as if the planet plays a hidden drumbeat, and the star responds with a burst of light. In some cases, the effect is like a cosmic aurora, a small, rotating hotspot on the star that directly tracks the planet's motion. Observations of ionized calcium light, a tracer of hot chromospheric plasma, have revealed moving bright regions on stars corresponding to the planet's position. The interplay is continual and energetic. Some hot Jupiters have magnetic fields many times stronger than Jupiter's, enough to power these stellar light shows. It is like the planet amplifies the star's magnetic orchestra, adding energy and excitement that the star would not have on its own. Beyond magnetism, gravity weaves another thread in the star-planet bond. The planet's immense gravity pulls subtly on the star's surface, injecting a bit of extra spin. Normally, a sun-like star spins down with age as its magnetic winds carry away angular momentum. But a close, massive planet can partially oppose this slowdown. For example, in wide binary systems where only one star has a hot Jupiter, the star with the planet often shows higher magnetic activity and a faster rotation than its twin. The giant planet appears to have kept its star more youthful by donating orbital momentum. A striking example of this gravitational influence is the system HATS 18. Its planet, HATS 18b, orbits in just under a day and is more than twice Jupiter's mass. The host star of HATS 18, however, spins roughly 3 times faster than expected for its age. The explanation seems to be that as HATS 18b's orbit decays under tidal forces, its lost angular momentum is deposited into the star. It's as if each orbit gives the star a little spin-up, like 2 dancers sharing steps. Over time, the planet grows more locked, and the star spins faster, preventing the star from aging as quickly as it normally would. In effect, the hot Jupiter's gravitational hand keeps pushing on the star, injecting fresh energy into its rotation. So the relationship is twofold. The planet's magnetism can light up the star's atmosphere, and its gravity can boost the star's spin. Both effects keep the star lively and active, forestalling the normal aging process. The star's corona may flare more often, its surface dotted with bright regions it otherwise wouldn't have. The star might emit extra X-rays or ultraviolet light, making it appear more energetic than a lone star of the same age. Hot Jupiters are like unseen conductors in a stellar symphony, subtly driving up the energy and tempo of the star's own performance. Early observations even hinted at dramatic star-planet interactions. For instance, HD 179949 was once reported to show a chromospheric hotspot rotating in sync with its hot Jupiter, and HD 189733A showed extra flares when its planet was at a particular phase. These early findings suggested the planets might stir magnetic flaring on the stars. Subsequent studies found the situation is complex, but the idea remains intriguing. On the whole, it appears that stars with hot Jupiters often have a bit more activity than similar stars without them. It's as if the planets keep the stars youthful. Even subtle effects can matter. A tidal bulge on the star itself may be raised by the planet's pull, though in sun-like stars this effect is usually slight compared to the star's own dynamics. The main takeaway is that hot Jupiters do not orbit silently. They leave their mark in the star's light and motion. These planetary giants not only endure their star's blaze, but they reach out to change the star in return through invisible magnetic threads and gravitational tugs. Yet these magnetic and gravitational tugs are only part of the story. There is a deeper exchange at work. Tidal forces, the gentle but persistent pull between star and planet. The star and planet interact with gravity much like the Earth and Moon do. Each raises tidal bulges on the other. If those bulges do not line up exactly, they create frictional torques. Over time, these torques transfer angular momentum between the orbit and the spins of the bodies. In effect, the two objects slowly exchange energy. As the planet's orbit decays, the star picks up some of that lost energy, and vice versa. This is the grip of tides, a slow but inescapable gravitational dance between the star and its hot Jupiter. In practical terms, these tidal bulges can act like cosmic brakes or engines on the orbit. Picture an ice skater. If the skater stretches out, she spins more slowly. Pulling in, she spins faster. Similarly, if the bulge on the star lags behind the planet, it tugs back on the planet's motion, draining its orbital energy. This generally happens for hot Jupiters because they often orbit faster than their stars rotate. The result is that the planet's orbit slowly shrinks. Conversely, if a star spins faster than the planet orbits, the bulge can push the planet outward, but in most known cases, the drag wins. Observations bear this out. We see evidence of shrinking orbits. For example, WASP-12b's period is steadily decreasing, as if an invisible hand is pulling it inward. Each orbit slightly drags the planet closer to the star. As this tide-induced drag continues, the changes are tiny but relentless. With each pass, the orbit is only minutely altered, but over millions of years, the effect is dramatic. A hot Jupiter's world slowly spirals inward, inch by cosmic inch. At the same time, the planet's own rotation usually locks in place. It ends up always showing the same face to the star. The days grow longer on the far side, until there is perpetual daylight on the starward face and eternal night on the far side. Meanwhile, the star may absorb some of that orbital momentum, aligning its spin axis with the planet's orbit and even accelerating its spin. The result is a long, slow crawl toward equilibrium, and often toward doom. Some extreme cases highlight the power of this exchange. TOI 2-109b, an ultra-hot Jupiter, 5 times the mass of Jupiter, whips around its star in just 16 hours. Observations show its period will shrink by about 10 seconds over the next 3 years. That tiny change per year may seem negligible, but it proves the planet is spiraling inward. If such shrinkage continues, the planet could eventually spiral into its star. Each orbit pulls it a bit closer, marking the planet's inexorable journey inward. It's the same physics that locks our moon's face toward Earth, taken to extreme scales. Over cosmic time, the fate of many hot Jupiters is as dramatic as their names suggest. For billions of years, their orbits are gradually eroded by these tidal forces. Each orbit steals a tiny bit of energy, and the planet drifts closer and closer to the star. Eventually, many are predicted to end in fire or debris. Astronomers are now beginning to catch glimpses of these final acts in progress. To capture this process, scientists monitor the orbits of hot Jupiters with extreme precision. Each time a planet transits its star, passing in front of it, we record the exact timing to fractions of a second. Over many years, even tiny drifts become apparent. So far, only a couple of planets show clear change. The planet WASP-12b, for example, has a definitively shrinking orbit. In contrast, some other extreme systems like WASP-18b or KELT-9b have not shown measurable decay yet. This suggests their stars may dissipate tidal energy less efficiently, or simply that more time is needed to see the effect. The diversity in these outcomes hints that not all hot Jupiters share the same fate on short timescales. Consider WASP-12b as a vivid example. It completes an orbit in just 1.09 days around its star, placing it extremely close. Over more than a decade of observations, each transit was found to occur slightly earlier than expected. The simplest explanation is a decaying orbit due to tidal forces. If this trend continues, WASP-12b will be pulled fully into its star in roughly 3.2 million years. We may literally be witnessing the final slivers of its cosmic life. Astronomers have even detected a cloud of escaping gas from WASP-12b, evidence it is losing mass as it falls. The planet is literally evaporating, shedding material like a comet as it spirals inward. We may be witnessing its final act as a hot Jupiter. Each orbit saps it a bit more, lighting up both star and planet with the energy of their slow tango. In fact, the rarity of extremely short-period gas giants, under 1 day, tells us many do not last long. Only the ones that migrate very recently or have weaker tides are seen today. This scarcity reinforces that tidal doom is a real phenomenon shaping exoplanet populations. In contrast, some hot Jupiters stubbornly hang on. Their orbits do not yet show a clear drift. This reminds us that orbital decay can be a patient process, and that different stars respond differently to their planet's tug. The long-term fate of many hot Jupiters is grim. Over eons of spiraling orbits, they edge inexorably closer to their stars. Each orbit bleeds a little energy, and the planet drifts inward. Eventually, many meet their demise, torn apart by tidal forces or consumed by their suns. Astronomers are now beginning to catch the first glimpses of these final acts in action. As these giants inch inward, one inevitable fate is stellar engulfment. Imagine a massive planet finally crossing the point of no return and plunging into its parent star. The collision would unleash a bright flash, converting the planet's mass into light and heat. Astronomers may have already witnessed such an event. In 2020, a mysterious transient called ZTF-SLRN 2020 briefly lit up the sky and was interpreted as a star swallowing a Jupiter-sized planet. While such planetary collisions are rare, they would be unmistakable. A star would flare dramatically, briefly shining more brightly before settling back to normal. If our telescopes catch another such flash, it could indeed be the death of a hot Jupiter, seen in real time. However, many hot Jupiters meet a different end. They are torn apart while still in orbit. If a planet drifts inside its Roche limit, the point where stellar gravity overcomes the planet's self-gravity, the star literally rips the planet apart. Instead of an immediate plunge, the planet becomes an extended cloud of gas and debris. Observations of some ultra-hot Jupiters show them trailing long tails of hydrogen, hinting at this slow disintegration. In such cases, the star is effectively eating the planet a little at a time. As the planet breaks apart, its shredded remains may circle the star before falling in. Any debris may be blown away by stellar radiation or winds. The planet fades away without a bang, dissolving into the star over time. The star may even temporarily show the elements of the planet on its surface before they blend back in, leaving only subtle traces. Another possible fate is for the giant planet to be stripped down to a core. As it loses its thick atmosphere, only the rocky or metallic core might remain, if it survives. Astronomers call such a remnant a chthonian planet. None is confirmed yet, but if one is found, it would be the leftover corpse of a hot Jupiter, essentially a gas giant turned to rock by stellar radiation. In effect, the final scene could be a large, scorched rocky world that once blazed as a gas giant. Ultimately, regardless of the pathway, a hot Jupiter's story ends with the planet gone. It may explode in brilliance, be shredded bit by bit, or gradually evaporate away. Observing these doomed ends teaches us about the power of stellar tides and gravity. Having glimpsed their fate, we now turn to a different kind of mystery in these systems. If these giants are so disruptive, why do they almost never have moons of their own? Unlike Jupiter in our solar system, which boasts dozens of moons, hot Jupiters roam the galaxy almost entirely alone. Every planet carves out a region of influence around itself, known as the Hill sphere, where its gravity dominates. But for a planet orbiting very close to its star, this safe zone is tiny. The star's pull extends almost as far as the planet's pull. For a hot Jupiter, the Hill sphere barely extends beyond the planet's immediate vicinity. This means that any sizable moon trying to orbit would be perilously close to the edge of falling out of orbit. Only something extremely small, comparable to an asteroid, could remain in a stable orbit within that narrow zone. Think of it this way. If Jupiter were moved to a point much closer to the Sun, its fleet of moons would be in trouble. The intense gravity of the star would yank them away or crush them against Jupiter. In practice, any large moon around a hot Jupiter would find itself either spiraling into the planet or escaping into orbit around the star. Tidal forces again play villain. The star raises powerful tides on any moon as well, heating it and distorting it. A large moon in a tight orbit around a hot Jupiter would feel these tides strongly, causing its orbit to change and likely decay. It would eventually spiral inward to hit the planet or be pulled outward past the Hill sphere, losing the battle for stability. Moreover, any moons that might have formed with the planet could have been lost long ago. During the planet's migration inward, its Hill sphere would have contracted. A moon that formed far out could have been left outside the shrunken Hill sphere and stripped away. Simulations confirm that when a giant planet moves closer to its star, it tends to shed its moons in the process. The planet's changing gravity and the star's pull would have likely ejected or destroyed most satellites. In effect, migrating giants are not kind to their moons. Some exotic scenarios have been considered where a moon might survive. For example, a moon in a retrograde orbit, going opposite the planet's spin, could, in theory, remain more stable under certain conditions. However, such orbits are rare, and even then, the moon would have to stay very close to the planet. The bottom line is that the stable zone for satellites around a hot Jupiter is extremely small, or effectively non-existent. Theoretical models show that any surviving satellites would have to be tiny. Observationally, this loneliness is confirmed. Dedicated searches for exomoons around hot Jupiters have turned up none. In fact, all of the tentative exomoon candidates discovered so far orbit cooler, more distant planets. Even one claimed detection of an exomoon around the hot Jupiter, WASP-12b, remains unconfirmed and highly debated. The lack of moons matches our theoretical expectations. The star's gravity simply does not allow big moons to persist. So the mystery of missing moons is solved by fundamental physics. Stellar tides and gravity leave hot Jupiters nearly moonless. Each hot Jupiter stands solitary, its sky empty of the companions we see around cold gas giants. This loneliness of hot Jupiters is remarkable. It speaks to the power of the star's pull close in. In a way, the absence of moons is another clue to the violent environment near the star. Despite their loneliness, hot Jupiters are far from irrelevant to their systems. Observers have noticed another pattern. Hot Jupiters usually have no neighboring planets in close orbits. When a hot Jupiter is present, astronomers typically find no other small worlds nearby. It is as if the giant planet has swept the inner system clean of rocky worlds and mini-Neptunes. This is no coincidence. Computer simulations make this clear. When a massive planet migrates inward, it tends to destabilize any smaller planets in its path. The migrating giant often crosses the orbits of inner planets on very eccentric paths and scatters them into the star or into distant orbits. Sometimes it collides with them or rips them apart. In all of these scenarios, the giant survives and ends up alone, while the smaller neighbors vanish. Detailed studies find essentially two outcomes for a migrating giant. Either it completely clears out the inner planets, leaving itself as the sole inner planet, or the giant itself is ejected. In practice, the outcome where the giant remains dominates for hot Jupiters. If a migrating giant could coexist peacefully with inner planets, it usually would not end up as a true hot Jupiter. In other words, for a gas giant to end up in a tight orbit, it almost always must have eliminated other worlds on the way. Rare exceptions exist, but they are very unusual. For example, the system WASP-47 is special because it has two small planets orbiting inside of a hot Jupiter. However, cases like WASP-47 are the exceptions that prove the rule. In general, when astronomers discover a hot Jupiter, they expect that the inner region is empty of other planets. The hot Jupiter has acted like a cosmic vacuum, clearing the inner realm. Even beyond the immediate inner planets, a hot Jupiter's influence can rearrange the entire system's architecture. If there are companion planets further out, the hot Jupiter can tilt or excite their orbits. In some systems, a distant planet may have triggered the giant's inward journey through gravitational interactions. Conversely, the hot Jupiter's presence can lock other planets into orbital resonances or destabilize them entirely. We do see hints of this in some exoplanetary systems. For instance, a hot Jupiter on a close orbit with a mysterious outer companion on an eccentric path. The giant's migration likely played a role in that configuration. In summary, a hot Jupiter reshapes its entire system. Where one might expect a family of inner planets, we often find just a solitary giant. Astronomers often say these planets are bad neighbors. They dominate and deplete the inner planetary community. The solitary hot Jupiters we observe are testament to their turbulent pasts, leaving behind quiet systems with only remnant architecture. Each hot Jupiter we discover tells a story of past upheaval. Its solitary nature is a fingerprint of a violent migration history. All of these tales of hot Jupiters make us wonder about our own solar system's giant. Jupiter, though slightly smaller than some exoplanet hot Jupiters, stayed at a comfortable 5.2 astronomical units from the Sun. It never migrated into a scorching orbit. This absence of a hot Jupiter in our backyard is itself a clue about planetary formation. If Jupiter had followed the hot Jupiter path, the inner solar system could have been unrecognizable. Such a migration might have scattered or prevented the formation of Earth and its neighbors. Remarkably, the lack of an interior giant may have been crucial for life on our planet. One leading theory explains Jupiter's stationary orbit. Saturn played the hero. According to the Grand TAC model, Jupiter may have initially migrated inward to around 1.5 astronomical units, but then Saturn arrived and changed the game. The gravitational interaction between Jupiter and Saturn halted Jupiter's inward journey and even reversed it. Together, the two giants then moved back outward like a sailboat tacking around a buoy. In this cosmic dance, Jupiter ultimately settled at its current location and Saturn at about 7 astronomical units. If Saturn had formed later or farther away, Jupiter might have continued inward, like the hot Jupiters we see around other stars. This orchestrated reversal ensured Jupiter and Saturn became safe harbours for the inner solar system. The two planets opened a gap in the gas disk, slowing further migration. The net result? Jupiter never became a hot Jupiter. Its presence in the outer system allowed the inner planets to form undisturbed. As a result, Venus, Earth, and Mars could accrete in relative peace. The gentle environment allowed these rocky worlds to come together. If Jupiter had become a hot Jupiter instead, it would have likely destroyed or consumed that material. In this way, Jupiter's steadiness is linked to our very existence. Other factors also helped keep Jupiter in place. The protoplanetary disk's properties and how Jupiter accreted gas may have limited its migration rate. Jupiter carved a wide gap in the solar nebula, reducing the torques that would drive it inward. There was likely no violent scattering event to send it on a plunging path. In contrast, many exoplanet systems appear to lack these stabilizing factors. Without a Saturn-like partner, or with a different disk mass and viscosity, those giants continued inward. Some systems might have lacked a second giant altogether, leaving the first giant with a clear path. Others may have had disks that dissipated before migration could take place. These differences highlight how a combination of factors prevented Jupiter's fall in our case. Our comparison emphasizes how diverse planetary outcomes can be. Jupiter's restrained history stands out among the variety of hot Jupiter systems. By studying many exoplanetary systems, we realize that the solar system's architecture is just one possibility. Learning why our system diverged, with Jupiter as a guardian rather than an invader, adds a crucial piece to the puzzle of planet formation. It is a reminder that sometimes it's the things that didn't happen that teach us the most. In a sense, the lesson is this. What hot Jupiters are to other stars, we were spared in our own. Each hot Jupiter shows us what can happen under extreme circumstances. Jupiter's calm path teaches us about what might have been and how a gentle configuration can allow small worlds and life to survive. As our cosmic journey continues, we carry this lesson forward. The contrasts between the wild and the tame prepare us to understand new systems. The next chapters of exploration will build on these clues, unraveling more of the mysteries of planet formation and the fates of worlds. The story of exoplanets began with a surprise. The first new worlds we glimpsed outside our solar system were not distant twins of Earth, but giant planets flying close to their stars. For centuries, astronomers imagined planets like Jupiter orbiting far from the Sun, but nature had other plans. These hot Jupiters came into view, not because we sought them, but because their immense size and tight orbits made them impossible to ignore. In the mid-1990s, two Swiss astronomers, Michel Mayor and Didier Queloz, announced a discovery that captivated the world's imagination. Using a sensitive technique, they had detected a planet around a sun-like star named 51 Pegasi. Instead of a gentle giant far out like Jupiter, this new planet circled 51 Pegasi in just 4 days, hugging its star so closely that its year took less time than our work week. It was the first confirmed planet orbiting a star like our Sun. 51 Pegasi b was a blazing hot Jupiter, a giant wrapped in scorching light, and its discovery marked a bold new chapter for astronomy. Why were hot Jupiters found first? The answer lies in our tools and in physics. Astronomers often rely on techniques that notice planets indirectly by seeing their effects on starlight. A massive planet close in exerts a strong gravitational tug, causing its star to wobble back and forth. Even a gentle tug creates a tiny Doppler shift in the star's light, and for a hot Jupiter, this wobble becomes much larger. Just like a strong dancer on a dark stage, a hot Jupiter makes its presence known as it pulls its parent star in a perceptible dance. These massive, tight-orbiting planets dominated the subtle signals early on, so they stood out above the rest. Another way planets reveal themselves is by briefly passing in front of their stars and dimming the light we see. The larger the planet, and the closer it orbits, the more obvious the dimming. Hot Jupiters, with their bloated gas envelopes and quick revolutions, can block a measurable slice of starlight. Early exoplanet surveys using the transit method favoured planets that created bigger shadows on their stars. In the humble beginnings of planet hunting, these techniques biased discoveries toward large, short-period worlds. In effect, these massive planets volunteered to be seen. Finding 51 Pegasi b in 1995 was like opening a floodgate. Suddenly, astronomers found dozens of similar giants in quick orbits around distant stars. Many of these were known by catalogue names like HD 189733b or WASP 12b, each one a scorching world in its own right. All shared a surprising trait. They zipped around their suns in only a few days or weeks. We learned that these hot Jupiters created noticeable wobbles and shadows for our telescopes to detect. Each new discovery, while remarkable, reminded us that our journey had only just begun. In fact, the first planets discovered outside our solar system were completely different. They orbited a pulsar, the dense remnant of a dead star. This was discovered in 1992 by astronomer Alexander Wolszczan and his colleagues. These pulsar planets were small worlds caught in an extreme cosmic environment, bombarded by intense radiation. Because life around a pulsar seemed impossible, many astronomers doubted planets could orbit ordinary stars. But 3 years later, 51 Pegasi b proved them wrong. Its discovery showed the universe was hiding all sorts of surprises, not just around pulsars, but around stars like our own sun. With the trailblazing hot Jupiters discovered, astronomers' catalogue of worlds began to grow rapidly. Telescopes and survey teams across the globe pivoted their efforts toward new horizons, scanning more stars with ever better tools. In the years following 1995, both ground-based and space observatories teamed up in the hunt. By the early 2000s, more planets were being found regularly, each one expanding the tapestry of our knowledge. The list of confirmed exoplanets grew steadily, and with each announcement, our sense of the cosmic census deepened. Before long, the first one became many, and our universe seemed to be filled with worlds of all sorts. On the ground, the Doppler technique continued to bear fruit. Dedicated instruments like HARPs in Chile became more precise, capable of detecting smaller wobbles. They found not only more hot Jupiters, but also giants on longer orbits, sometimes taking years to circle their stars. Planet hunting teams extended their surveys to fainter stars and discovered massive planets in systems like 47 Ursae Majoris and 70 Virginis. Each new finding enriched our catalogue of faraway giants. These radial velocity surveys also began to uncover lighter worlds. Tiny Neptune-class planets and even super-Earths, a few times the mass of Earth, began to emerge from the data. Some stars revealed full systems of planets. 55 Cancri, for example, showed off 5 worlds, including a hot Neptune. As the catalogue swelled, astronomers realized the galaxy was teeming with planets of various sizes, not just the largest gas giants. Astronomers also began examining a wider variety of stars. Red dwarf stars, smaller and cooler than the Sun, turned out to be rich in planets. For example, Gliese 581, a red dwarf 20 light-years away, was found to host a system of planets, including super-Earths in its habitable zone. These findings showed that worlds abound, even around stars very different from our Sun. Meanwhile, another technique was launching discoveries: the transit method. In 1999, astronomers caught sight of the first star dimmed by a passing planet, confirming HD 209458b as a hot Jupiter. Soon after, new sky surveys began scanning thousands of stars for such shadows. Projects with names like OGLE, Super WASP, and HATNet sprang up, each monitoring wide fields of stars night after night. They found many more hot Jupiters, and even some smaller companions. The transit method allowed scientists to measure the sizes of these worlds directly, adding a new dimension to the catalogue of known planets. The space age of exoplanet discovery dawned in the 2000s. In 2006, the CoRoT Space Telescope began scanning the sky for transiting planets. CoRoT and similar space missions found dozens of new worlds, even pinning down the first ever rocky exoplanet, a small world called CoRoT 7b. But the real revolution came with NASA's Kepler Space Telescope, launched that same year. Kepler stared at a patch of sky for 4 years, recording the tiny dips caused by thousands of planets orbiting distant stars. It revealed new classes of worlds, super-Earths and mini-Neptunes, and sent our catalogue of known planets soaring from hundreds into the thousands. As the 2010s unfolded, the catalogue kept expanding. The Kepler mission alone discovered over 2,000 planets and validated thousands more candidates. Meanwhile, NASA's TESS mission, launched in 2018, set out to survey the whole sky for planets around the nearest bright stars. TESS has already added many more exoplanets to our list, often finding smaller worlds that are easier to study with follow-up telescopes. On the ground, advanced radial velocity instruments continued to push the boundaries of detection, finding ever smaller planets. Each new addition to the catalogue broadened our understanding of planetary systems. By the mid-2020s, our list included thousands of exoplanets, from massive gas giants to tiny rocky worlds, all around stars of many kinds. Some exoplanets have even been photographed directly. Using the sharpest telescopes, astronomers have imaged a few bright, young giants that glow in infrared light. One star, HR 8799, is famous for showing 4 massive planets in orbit, all captured in a single image. Another is Beta Pictoris b, seen moving against its star's glare over years of observation. These early images of distant worlds added exotic examples to the catalogue, proving we can sometimes see planets themselves, not just their shadows or wobbles in starlight. Planets also turned up in some of the strangest orbits of all. For example, several worlds were found orbiting 2 stars at once. In 2011, astronomers confirmed Kepler 16b, a Saturn-sized planet circling a pair of suns like a real-life Tatooine. Other circumbinary planets followed in the years after, proving nature can build planets in binary star systems too. These discoveries showed that stable orbits exist even amid complex stellar dances. Each of these binary star planets broadened our understanding of the cosmos, showing the universe is far more inventive than our solar system alone might suggest. Astronomers also found planets by a lucky trick of gravity. In gravitational microlensing, a massive star can act like a lens and briefly brighten a more distant star. If that foreground star has a planet, the planet's gravity causes a telltale extra blip in the light. Using this method, surveys like OGLE and MOA have discovered planets that are otherwise impossible to see, including possible planets floating alone in space with no parent star. These chance discoveries added to the growing census of known worlds. From scorching gas giants to frigid small worlds, from lonely rogues to rocky Earth-sized planets, our catalogue began to include nearly every kind of world imaginable. We found planets around massive burning stars and around tiny cool red dwarfs, in lone orbits and in elegant multi-planet systems. We even saw planets surviving around stellar remnants like pulsars and white dwarfs. The collection of confirmed exoplanets had grown far beyond anything astronomers had imagined back in 1995. Each new entry made it clear that the hot Jupiters had been only the first hints of a much richer cosmic menagerie waiting to be explored. By the mid-2000s, discoveries reached even the smallest signatures. In 2016, astronomers announced Proxima b, an Earth-mass planet orbiting in the habitable zone of Proxima Centauri, our nearest stellar neighbour, about 4 light-years away. This tiny world showed that even the faintest stellar wobble could be measured. Soon after, in 2017, the TRAPPIST-1 system emerged as a milestone. It contained 7 Earth-sized planets, 3 of them in the temperate zone, all orbiting a small, cool star. It was the first time so many Earth-like worlds were found around a single star. These astounding discoveries underscored how richly varied and surprising the exoplanet catalogue had become. The hunt for new worlds became a global effort. Robotically controlled telescopes from Chile to the Canary Islands joined the search, keeping a vigilant watch on the stars. Every night, observatories around the world streamed data to astronomers, looking for the slightest hints of distant planets. This coordinated network meant that the trickle of discoveries turned into a steady stream. Scientists published new planet announcements regularly, and even amateur stargazers with backyard telescopes contributed to the discoveries. Our growing catalogue owed itself to this worldwide effort. Hot Jupiters were just the vanguard of exoplanet discoveries. As our catalogue grew, it became clear that these giant scorched planets were only one flavour in a vast cosmic spectrum. Many other types of planets came into view, spanning a range of sizes and compositions. Some were rocky and small like Earth, while others were gaseous like Neptune or even larger. We saw planets in nearly every size class, from sub-Earths to massive super-Jupiters. In fact, the most common new worlds turned out to be those between Earth and Neptune in size, categories our own solar system lacks. Beyond these giants, we uncovered a rich menagerie of planetary types. One of the biggest surprises was how abundant super-Earths and mini-Neptunes proved to be. These planets are larger than Earth, but smaller than Neptune, a size range our own system lacks. Many stars host several of these intermediate worlds. Some are scaled-up rocky planets, while others hold on to thick gaseous envelopes. Astronomers realized they had to expand their categories. A planet a few times Earth size might be an oversized rocky world, or a gas-enshrouded mini-Neptune. This blurs the line between terrestrial and gaseous worlds, illustrating the richness of exoplanet diversity. Astronomers also found planets that, in size and orbit, resemble scaled-up Earths. Some inhabit their star's temperate zone, where liquid water could exist. For example, Kepler 186f is roughly Earth-sized and orbits in the habitable zone of its star. The TRAPPIST-1 system provided multiple Earth-sized worlds, with 3 of them in the habitable zone of a cool dwarf. Even a super-Earth called K218b, orbiting a red dwarf, has shown evidence of water vapor. Each such discovery hints that rocky, water-friendly planets might not be rare in our galaxy. On the other end of the scale, astronomers found many gas giants far from their stars, more like Jupiter and Saturn in our own system. Long-term observations revealed planets orbiting at several astronomical units on multi-year paths. Some star systems even host multiple gas giants, reminiscent of our own. For example, 47 Ursae Majoris has a Jupiter-like planet at about 2 astronomical units and another farther out. These cold Jupiters are not scorched by their suns, suggesting that gas giants can form and remain at a distance, much like the giants in our own solar system. Even within each class, exoplanets display wild variations. Some ultra-hot Jupiters, like KELT 9b, orbit so close to their stars that their dayside temperatures reach around 4,000 degrees Celsius, hot enough to vaporize metals. Others, such as WASP 12b, are being torn apart by their star's gravity. Planets on elongated orbits, like HD 80606b, swing between freezing and scorching conditions. Among smaller worlds, we found lava planets, such as 55 Cancri e, which likely have molten surfaces. Each new world seems to have its own quirks, a reminder that nature's variety knows few bounds. The diversity extends beyond any single category. Surveys have even detected rogue planets wandering the galaxy with no star to call home, revealed through gravitational lensing events. At the opposite extreme, extremely massive objects blur the line between planets and brown dwarfs. We also see planets surviving around stellar remnants. For example, gas giants orbit pulsars or white dwarfs. All these findings underscore that planets come in so many flavors and can thrive in an astonishing range of environments. The endless variety of exoplanets teaches us that nature's creativity often exceeds our imagination. Hot Jupiters have become natural laboratories for understanding extreme planetary physics. In their glowing atmospheres, atoms split and novel molecules form under blistering temperatures. Astronomers have detected exotic compounds in their gases, from sodium and water vapor to titanium oxide, at temperatures exceeding 1,000 degrees. Intense stellar radiation drives powerful winds, circling these planets at speeds of thousands of kilometers per hour. Each measurement, such as phase curves or Doppler shifts, tests our models of atmospheric dynamics under conditions impossible to reproduce on Earth. Their interiors challenge theory as well. Many hot Jupiters are larger than expected from cooling models, a phenomenon known as radius inflation. This mystery has prompted ideas like ohmic heating, where intense radiation induces electrical currents that heat the planet's interior from within. Another possibility is that ongoing tidal interactions with the star inject extra energy by comparing their measured sizes and temperatures against models. Scientists glean clues about the exotic states of hydrogen and other materials deep inside these giants. Hot Jupiters also provide testbeds for star-planet interactions. Their immense gravity raises tides on their host stars and can spin stars up over time. In some cases, a star's rotation appears synchronized with the planet's orbit, hinting at strong tidal coupling. Researchers are also exploring magnetic effects, for instance, observing whether a planet's magnetic field triggers extra activity on its star. These phenomena let us explore tidal physics and magnetism in new ways, extending our understanding of how a close companion can influence a star. The study of hot Jupiters also advances our understanding of chemistry under extreme conditions. By observing transits, astronomers have analyzed starlight filtered through their atmospheres. They have detected atomic and molecular species, like water vapor, carbon monoxide, and even metal atoms, even at temperatures of thousands of degrees. Each detection tests our models of chemistry and physics at pressures and temperatures far beyond anything in Earth's laboratories. In short, every hot Jupiter is a cosmic experiment. They allow us to test physics, fluid dynamics, chemistry, and magnetism at the limits. They inspire new theories and challenge old ones. In that sense, each new one found is like adding a point of data to a grand experiment conducted by the cosmos. The next decade promises to expand our view of exoplanets dramatically. The James Webb Space Telescope, JWST, already operating in space, can probe exoplanet atmospheres in infrared light, detecting molecules like water and methane with unprecedented sensitivity. Soon, the European aerial mission will carry out a census of exoplanet atmospheres, examining hundreds of planets for their thermal profiles and chemical makeup. These space observatories will turn our small sample of studied planets into a vast database, revealing exoplanet weather and chemistry in exquisite detail. New missions will also find many more planets. ESA's Plato mission, planned mid-2020s, will search for Earth-sized planets around Sun-like stars, focusing on bright stars where follow-up studies are easy. NASA's Nancy Grace Roman Telescope will use gravitational microlensing to discover thousands of planets, including many cold and free-floating ones. On the ground, next-generation spectrographs like Espresso and Express will push radial velocity sensitivity down to a few tens of centimeters per second, aiming to detect true Earth mass planets. Even the smallest worlds that today hide in the noise will soon become visible. Giant telescopes are on the horizon too. The extremely large telescope, the Giant Magellan Telescope, and the 30-meter telescope, all under construction, will revolutionize direct imaging of exoplanets. Equipped with advanced coronagraphs and adaptive optics, they may capture actual images of Jupiter-like planets around nearby stars and even spot bright glints from Earth-like worlds. These ground-based giants, combined with space missions, will offer a new view of distant worlds. We may soon begin to map alien continents and search for signs of life directly in the light from another planet. Beyond these projects, more ambitious ideas are taking shape. Concepts like starshade missions or space interferometer arrays could eventually image true Earth analogues in the habitable zones of nearby stars. Meanwhile, new radio astronomy techniques might detect magnetic fields or lightning on distant worlds. Whatever the future telescope or instrument, the one certainty is that each will uncover surprises. The horizon of discovery continues to expand, ensuring that the story of exoplanets will keep unfolding for decades to come. Hot Jupiters have taught us to expect the unexpected in the cosmos. Before their discovery, scientists never imagined that gas giants could lurk so close to their stars. Their existence forced theorists to rethink how planets form and move. Each new hot Jupiter reminded astronomers that nature does not always follow our expectations. It was a lesson in humility. The universe can be more creative and diverse than our models predicted. These exotic worlds stand as proof that the universe always has surprises in store. Just as pioneers expanded our maps of the Earth, each hot Jupiter showed us a new piece of the cosmic puzzle. They taught us that planetary systems can take many paths, and that answers often come from listening to what the universe shows us, not just what we predict. With every planet discovered, We learn to question assumptions and stay open to wonder. The story of hot Jupiters is still unfolding, and it inspires us to press on. Even now, astronomers marvel at how these blazing giants defy the norms. They remind us to look at the stars with curiosity, always expecting something new. And as we continue to explore, each surprise reaffirms one truth. The universe is far more extraordinary and unpredictable than we can imagine. The wonder is far from over, and the next chapter of discovery is just beginning.